Testing, testing. Hello, testing. Hello. It is working. Was that you? Okay, thanks everybody for coming. It should be a great workshop. There's lots of people here. It's great to see you all. My name's John. I'd just like to give you a few slides to welcome you to the workshop. So we have 15 accepted papers, which is fewer than Popple. So I don't know if that's... the list of participants as of a couple of days ago is available at the front here. There are lots of copies, so feel free to take one. There are also some reprogrammable name badges on the front table as well. If you could all put a name badge on, that would be great. If anybody doesn't have EduRoam, we have some guest Wi-Fi username and password tuples. And they're on a piece of paper at the front there. So you just, there's a list of 40 or so. Just cross off a username and password when you've taken it, and that should work itself. There is a schedule which is also printed out there. It's online as well on the web page. Let's guess Wi-Fi. This evening we'll be going, anybody who wants to come for dinner is very welcome to come at the Med Kitchen, which is maybe 10-minute walk away. That's at 7 o'clock. Before that, anybody who wants to is also welcome to go to the pub. And I thought it would be nice to go to the Imperial College Union, which is, it's called the Bite Bar for any Imperial locals. So that it should be quite easy to follow an Imperial local, and they'll take you there. There aren't many students here at this time of year, so it's nice and quiet. Finally, I'd like to thank my co-organisers, Azalea, Ali, and Philippa. So we're all here if anybody has any questions or needs any help. I think that's about it from me. I mean, if there's a fire, that's probably because somebody compiled a program that has a data race. So don't worry about that. And so I'll just hand over to Azalea briefly, who is going to tell you about some live streaming.
So there isn't really much to say, except that please, even if I forget, remember to hand over the microphone, because without it, our virtual audience will have no audio, because the voice is really, the audio is really weak otherwise. So remember to take this over, and if you don't want to be streamed or recorded, just tell me and I'll switch off the stream. And finally, if you want to be in the shot, please stand here. We have a clicker, so you don't really need to be next to your laptop. So if you stand here, you're in the shot, and of course the slides are in the shot. Around here. Yep, yeah, good. Thank you. Good, I have my tiny little helpers. Excellent. And that's it. So I would like to invite our first speakers to come over and give the amazing talk. And please remember to hand this over. And you can put this anywhere, in the pocket, clip it on, wherever it's more comfortable.
Okay, thanks.
Nice.
Yeah, the nice thing about being the first speaker is that I can do Decker's example, which is like, I tried this several times. Did you switch it? I mean, did you change anything? OK. So my name is Roland, and I will talk about robustness, which is a criterion, correctness criterion for concurrent programs running on relaxed memory models. OK, so we're in the business of decidability and complexity. So therefore, I will assume that sort of all the data that we have in the program is finite, right? So it's like we have a finite set of shared variables that I will call x, y, and so on. And there is a finite data domain, and I will only talk about Booleans here. And when we talk about threads, I mean finite control, right? I mean, it's essentially while loops, OK? And this is the prototypical example that you would like to have correct under a relaxed memory model, which is called Decker's mutex. So you have two threads. And what they want to do is they want to visit their critical section. And they do so by saying, I mean, everybody has a variable and says, I have an interest in visiting my critical section, checks that the variable of the other guy is low, and in case just goes, OK? And the question is, does this guarantee mutual exclusion? Well, this depends on the machine that you run this program on. Of course, you know all this, right? But because I'm the first talk, I can maybe bring us all to the same level. And I will need some way of how I think about these programs, which is sort of in terms of linear orders. So if you have their C semantics, then to my understanding, this corresponds to the interleaving of the languages of the single threads, OK? So what is the interleaving? It's just the shuffle of the actions that you see in each thread. So here's the configuration of the threads on the right-hand side. So PC is the program counter, and A is the next command to be executed in the first thread. And if we run this under SC, what will happen is that we set x to 1, and this will be visible in the memory like immediately. OK, so we do this step. We have the program counter set to B, and x is 1 in the memory. What you see is that in the computation, I put the fact that we have an issue of the command, and the command becomes visible in memory. So these are two events that in SC happen atomically. OK, and this will not be true under more relaxed memory models. So next, what the thread does is it will check that y is low, right? Which is true, and the program counter evolves to C. So the first thread is now in the critical section. The second thread comes, the program counter is at P, will set y to 1. And again, we have an issue action and immediately the write command visible on the main memory. OK? And now the second thread would like to see that x is low, but this is no longer true. So what we have is that the computation ends here and mutual exclusion holds. OK? So SC is nice and intuitive and so on, but it just doesn't exist. OK? So what you would like to do is the compiler would like to move commands out of loops, or sort of the hardware would like to do further optimization. So an optimization that hardware may want to do is you have a write buffer in front of the memory, and what you want to do is you want to do batch processing with your writes. So you move a whole bunch of writes into the memory in one shot. OK? And if you do this, you get more relaxed behavior. What we will talk about in this talk is total store ordering, which is the behavior of x86 machines, like nowadays this Apple thing. So a TSO architecture has a write buffer. And if you have buffered a write, what the read will do is it will first look at your buffer, whether it has a write on the variable that you're interested in reading. In case it gets the value from that read. And otherwise, it sort of overtakes the write that is buffered, and it looks into the main memory. And if we now have a look at Decker's example, we have this strange behavior. So again, the first thread will say, I'm executing the command at program counter A. OK? Which just now means I'm just issuing the command. It's not yet visible on main memory. OK? Now the thread will read that y is 0. It will actually be successful. It will sort of pass by the write on x that is buffered. We'll look into the main memory. Y is 0. Well, fine. And then it enters the critical section. OK? So we can just execute the read on y. The second thread comes and says, well, I'm issuing a write on y. And then the memory subsystem would say, oh, yes, and I have time to perform this write on y on the main memory. OK? So we also see the write on y. Now comes a read on X. So the buffer is empty. We first check the buffer for a write on X. There's nothing in the second buffer. And we look into the main memory. Well, and in the main memory, X is still low, right? So the second thread can read 0 from X. So you should note that the second thread cannot inspect the local buffer of the first thread. I mean, this would ruin all your performance gains of this. And finally, we write X to 1. So what you see by this is that if you run this program on a TSO architecture, mutex will fail, right? And it fails because you can have a delay of this form. So you have an issue, but the associated write on X is some time later. And this sort of notion of, how to say, this nesting edges that associate the two parts of the same command with each other, they will play a crucial role in the rest of the talk. OK. So what you see is that relaxed executions may lead to bad behavior. I mean, behavior that was not expected. And you can say, OK, like if this is what is happening, like why should anything work in this world, right? I mean, why can we program machines of this form? And the answer is there's a nice theorem that says, well, if your program is data race free, then you have the guarantee that the TSO and the sort of SC semantics will coincide. And this is a result that holds for sort of any reasonable architecture. OK, I mean, it's sort of a guiding principle that programming language designers and hardware architects agreed upon. OK? Well, you may say, then just write data race-free programs. OK? I mean, and that's it, right? And this is actually true, right? I mean, this is the answer that, OK, now I made up the number. But this is the answer that should hold for 90% of the cases. Like, I mean, if you program like whatever stupid, let's say, Word or what, you don't care about having it as fast as possible. Just make it data race free. OK? It doesn't work for performance critical code. OK? Performance critical code, if you write a concurrency library and you're Doug Lee, or you write an operating system, or like if I talk to the HPC guys at Fraunhofer, so they will say, oh, look, we write racy code. I mean, as long as it's fast, this is what we want. OK? So, I mean, one has to be aware of the fact that the people that we do verification for are like these 10% that don't fall into this. I mean, also by this, my opinion would be that we need more sort of techniques that check data race freedom, but it's not so popular these days. OK, so the idea of robustness is to say, so what is the spec? The spec is really the SC semantics. This is what the programmer had in mind. And so relaxed behavior will have bugs just because it's executed in a way that's different from SC. So what we want is that if we have relaxed behavior, there is an equivalent. And the question is, what is this notion of equivalence? And to have particularly relaxed programs, we would also like to have a weak notion of equivalence. Yeah, under SC. OK? Taking a relaxed behavior, SC has a behavior that is similar. And similar will mean it has the same happens before trace. OK, and phrased differently, our sort of idea of this is if you deviate from SC, then this is a programming error. OK, and as I said, sort of decidability and complexity means we formulate the problem precisely. What is given to you as an input is a program. And the question that we're asking is the trace semantics under the relaxed memory model contained in the trace semantics under SC? And the reverse inclusion trivially holds because you could just write something to the buffer and it immediately goes to memory. So what is the decidability and complexity of this? And what I will talk about is a solution. So we have been working on this for a while, and there are different solutions for TSO, PGAS, power, and so on. There's a very general principle. General comes with a small remark. This is a principle that will give you the precise complexity of the problems. It's not what you would like to implement in a static analysis tool, but at least you know how hard the problems are. OK? And what I will talk about is from ICAL 14. So it's a decision procedure that will apply to sort of every memory model that we have considered, like TSO, PSO, PGAS, and power, like in this JUD formulation of like a year ago, herding cats. OK, it gives you the precise complexity. What is not so nice is you will need a new automaton model for this. And new automaton model means it has a lot of guessing involved. OK? I mean, if you do polynomial space, there's a lot of space for guessing. Let's put it that way. So the general principle looks like this. So here you have the robust computations. and there's the space of all the relaxed computations that your program may exhibit. And what you want to know is whether there is a computation that is not robust, right? Well, if there are not non-robust computations, there are some that are minimal, okay? And the notion of minimality we have to discuss, right? I mean, there are different minimality criteria that you can pose, and you get different and nicer results depending on how sort of subtle your minimality is. So we will talk here just about shortest violations. Already this gives you something. So what you immediately see is you're not robust if and only if there's no minimal violation, right? If there are violations, then there are minimal ones. So our study will have a combinatorial part that says, give me a minimal violation. I will tell you it has a certain normal form. It's not an arbitrary computation, an arbitrary relaxed computations, but it's very ordered, let's say. It does delays in a very ordered form. And then in the second step, we need an algorithm that tells you whether or not you have violations of this normal form. Okay? So what we will end up with is an emptiness check of this form. Okay? Just to repeat, combinatorial reasoning. If there's a violation to SC, then there is one in normal form. So what do we mean with this intersection? So the algorithmics is actually a formal language emptiness problem. We have the language L and F, which consists of all normal form computations. But you don't know whether they are harmful or not. So you do an intersection with a regular language that will filter out those that are cyclic, that are violating. Okay? And in the end, we have an emptiness check to do. Good. So let's understand what the violations to SC would look like. So there's a Shasha-Sneer lemma that is very useful for us that says a violation, a computation is not an SC computation if and only if the happens before dependencies are cyclic. Okay? And what are the happens before dependencies? Well, so given a sequential computation of this form, we associate with it a partial order. How do we do this? Well, we preserve a bunch of things that say, up to permutations of these relations, the execution is independent of permutations of things that are not related by these relations. So what are these relations? It's program order, right? We said the write on X has to come before the read on Y in the first thread. And in the second thread, it's the same. I'm just drawing it the other way around to see the cycle. OK. There's another ordering that says, for each variable, what was the ordering on stores that we saw? OK? So here I'm making some initial notes that say, initially we had some value x equals 0 or what. OK? And it was overwritten by the write x1. And we had an initial value for y, and it was overwritten by the write y1. OK. There's a source relation, or you may call it read from. Oh, the store order you will also call coherence order, right? This is what we all mean by this. OK, it's store order, coherence, it's all the same thing. So read from, I call it source relation. What is the write that the read reads its value from? So here you would see that the read x0, it gets the initial value, right? Because nobody has written to x so far. So we have a source edge there. Good. And there's a you see you have the read x0, and it gets overwritten by the following write x1. Therefore, we will have this conflict edge. Good. And as you can see, this is an execution that is not valid under SC, because it has this nice cycle PO conflict. Good. So the first fact that we see is, there's a violation if and only if there's one in normal form. The normal form will be a computation that consists of two parts, tau1 and tau2. In each of the parts, there are no delays. And the crucial restriction is that if you delay something from tau1 to tau2, the writes will occur in the same order in which the issues occurred here. OK, let's do a figure. Can we understand that this is a normal form? OK, so the blue issue was before the red issue. So the corresponding writes, the corresponding blue write should be before the corresponding red write. And with a bit of algorithmics in mind, you already see that this sort of lends to stream processing of the computation, right? I mean, it's like you can read it without having to store. So what would not be in normal form? So something like this is not a normal form computation, okay? We have a later issue, but the write is performed earlier. So in terms of algorithmics, this would be very bad for you, right? Because you would have to store all these guys on a kind of stack, and later on see all the writes. Okay, so normal form computations have this sort of ordered delays. How can we show that we always have these guys? Well, so what we want to show is if a program is not robust, it has a violation in normal form. Okay, take a shortest computation that has a cyclic happens before relation. Now you have to show that there is an event that you can cut out, like one action, one command, and the result is still a feasible computation. Whether or not you can do this heavily depends on the memory model. So you can do this for TSO, PGAS, Power, and PSO. You cannot do this if you have out of thin air values. So this is where out of thin air comes a bit into play. Okay, because I mean, out of thin air means essentially the cycles lying to each other, right? I mean, I can do the read because I will read, yeah. I mean, I have reads that depend on writes that will be issued later. Okay. There is an event that you can cancel. Whether or not this holds depends highly on out of thin air values. Now look at the computation where you cancel the event. Well, in particular, it's missing the event, so it's shorter. So what can you conclude? Well, it cannot be violating, right? But because it's not violating, it means that you will have an SC equivalent computation. Okay? And now what you do is you project the SC computation to the actions that you had in the first part of the computation. Then you reinsert the event that you deleted, and you project to the second part of the computation. And this will be in normal form, and it will have the same trace as your original computation. And of course, it will do you the favor that it is in normal form. I mean, just to see this. Yeah, OK. So let's say we have issue write, and now we project these two actions to the left and these two actions to the right. OK, what we get is this issue is delayed until here, and that write is delayed until there. So this is the intuition why it is in normal form. OK. What we now need is a class of languages that allows you to represent such computations. Well, there's a wish list of properties that this class should have, right? So the language should first include all normal form computations. This is for sure. Otherwise, we cannot represent all of them. It also has to be closed under a regular intersection because we have to find cycles. And it should have a decidable emptiness problem because otherwise we're also doomed. OK? And I mean, you cannot just take the regular language or the context-free languages, because what you will get is you can have a bunch of issues, and later comes the bunch of corresponding writes. And in terms of formal languages, this is the language of sort of word sigma followed by sigma. And this is not a context-free language. So you need some different machinery to represent it. OK, not context-free. And the machinery that we take is, we call it a multi-headed automaton. OK? I mean, after all, our computation just has two parts. Why not take a finite automaton that has two heads? OK? So it's an extension of finite automata that will generate the two parts simultaneously. And the transition will say, I am adding the A to the first part of the computation. Or it will say, I'm adding the A to the second, or the B to the second part of the computation. So if you do this on this example, here are the two heads. As long as we have independent actions, we can just read them. OK, I'm moving the head now, so this is maybe not so good to see. And now you can see how we can delay a write. So delaying a write just means I'm issuing the command on the first part of the computation, and immediately with the next transition, I'm doing the corresponding write. OK? Good. And maybe I should skip the cycle chasing. I mean, essentially, the point is there are finitely many cycles. You guess the crossing edges between two threads. And guessing one such edge just amounts to a regular intersection. It will just say, sigma star, I don't care. Now I see the read. Now I see the write. And I accept. And because the cycle types are kind of finite, I can do this with a finite intersection. Good. And emptiness is just the same as emptiness for finite automata. OK, so what you get is robustness is p-space complete, which is, in terms of verification, it's the best complexity that you may hope for, right? I mean, as long as you have Boolean variables, you really take the variables into account. It's like you cannot get below p-space because a bunch of Booleans already is a Turing machine of linear size. So the upper bound is this emptiness problem. The lower bound is state reachability, right? I mean, it's like robustness is the same as taking one thread, saying, I am interested in this control location, and then you make a new thread and you append a Decker cycle here. This is the lower bound. OK, thanks. That's it.
Thanks very much, by the way, for a great introductory talk. I'm very glad I scheduled you first. I was just wondering if, so you gave the example of Decker's algorithm, and this breaks as soon as you have any sort of relaxed behaviors.
Yeah.
I was just wondering if you were to have an algorithm that perhaps was a bit less sensitive than Decker's algorithm, where you don't want certain relaxed behaviors, but you could tolerate some behaviors that are not SC.
Yeah.
And is it the case then if your technique would say no, that's just...
I mean, I wouldn't know how to handle it. So what you would need to do is you would, I mean, the things that you don't want to be sensitive to, you really have to do the TSO semantics for this. And it's understood how to do this nowadays, but sort of the complexity for TSO reachability is non-primitive recursive, like hard. And this means it's as good as undecidable. So it's like, I mean, one can prove a result, most likely, that shows, oh yeah, it's if and this is reachable in a machine that has TSO buffers. But then you would definitely have to approximate something because you cannot check it in a complete way. Yeah. I mean, what may also be interesting, I mean, I know that sort of in sort of program logics may be a popular topic here. Results of this form may be interesting to get completeness results, like up to handling of the data, because you know what are the patterns that you would need to look for. So it's essentially you compile away the whole relaxed business until you arrive at something that is more or less SC. I mean, this is a vague claim, maybe you could immediately kill me for that, but there may be a chance. Yeah.
Results of this form may be interesting to get
yeah.
Yeah,
yeah, so there's a story about fences. So, I mean, for this, we... The point is that we are... OK, now I get what you say. The story about fences... OK, the selling point is, of course, we know how to get from this a fence insertion algorithm, and it will compute the optimal number of fences, blah, blah, blah. But what is really true is that because you want to establish robustness with respect to SC, fences will have no effect. So all that I have to do is I have to restrict my set of computations that I'm considering so that in the computations I will have the fences. But, I mean, my trace is an SC trace. So I have strong program order. So you could decide to make a similar story as we are doing here, and you say, I want my program to be robust from power to TSO, which may be a sensible thing to do. So I developed a library, and I carefully tested it to run on x86. But now I want to port it to power. So what you then would have to do is, you would have to say, oh, I don't have the SC traces, but I have TSO traces. And then you would need to say, what is the effect of a fence and so on. Yeah, and you would need to adapt the notion of trace, but you would know how to do that. Yeah.
which may be a sensible thing to do. So I developed a library.
Yes.
And I carefully
How do you do it for
run
power?
x86.
For non-store
Now I want to call
atomicity?
it power.
You split it into several actions. So first, I mean, the power semantics is way more involved. I mean, it's like, okay, here I'm telling like not even half of the story. So it's like you don't have writes and reads. So you have loads and stores, and you have local computations and so on. And if you want to do a store, it's like you have to check that everything that you depend on, I mean, or you want to do a load, let's say. You can correct me anytime on the power semantics. So first you have to make sure that you can load the value. So you have loaded the value. Then you have computed the value that you have. So an action is issued. It loads the dependencies. It computes. It commits. And then, this is the main point that you're asking for, it propagates to all the threads that are in the system. So you will have one memory action per thread. Okay, to cut a long story short, I mean, an approximate model would say, issue something, commit it, and propagate it to every single thread on its own. But, I mean, there's also this loading and computing part. So, and there was a paper by Mador Haim, and wasn't you guys involved in this? That says this is the axiomatic model of power. I mean, this is the way you do it. So it's like you have a separate node for each of the propagate actions.
And you still have the nice property with the normal forms.
Yes, the normal form stuff holds. It's, of course, not a normal form that... So what you cut out is you cut out a full action with its commit action and with all the memory actions. Let's say you have m threads. This will give you m plus 1 or 2 or 3 parts of the computation. But still, then you don't do it with a 2-headed automaton, but with a m plus 3-headed automaton. But also this means that if you want to do it in the unbounded case, this technique will not work. Okay.
Thank you very much.
Yeah, thank you. Oh, this was the warning.
The next up is not Raymond, who it's a last-minute change to Julien Lange.
Hello. So I'm going to talk about a work that was published this year at Purple. It's a joint work with Emilio Tuosto from the University of Leicester and Nobuko Ishida from Imperial. And I always start this talk with this little analogy. So you might know about algorithms based on the flocking behavior of birds. And the idea of those algorithms is that if you give some rules to a single bird, you actually obtain something that is quite surprising. For instance, if you give those 3 rules to a bird, saying that it shouldn't be too close to its neighbors, it should follow head towards the center of mass of the whole flock and steer towards the directions of its neighbors, then we get a flocking behavior. So in the sense of this work, a single bird is a local behavior or a communicating finite state machine. So we'll explain what those are. And the idea of those flocking algorithms is that if you compose several birds with those rules, you obtain actually this V-shape formation. So it's a global behavior that emerges from local rules, in a sense. So you have a set of local specifications that give rise to a global behavior that in our field we call choreography. So a choreography is a specification of the distributed system from a global point of view, so where the whole system is specified at once, in a sense. Yeah, so this work is about building a view, a global view. And we have several motivations to do that. On one hand, we have some practical industrial motivations, and on the other hand, theoretical ones. And on the practical side, the idea is that distributed systems generally last for quite a while in industry. So you might have web services that last for 10, 20 years. And generally they do evolve, even though they might be designed in one point at some point in their, when they're first designed. But then later on, each bit of the distributed system might evolve separately. And the documentation is generally not maintained in a coordinated way. And then sometimes in service-oriented systems, for instance, services are dynamically composed. So again, in those situations, we have no idea what the system looks like. And with our partnership with Cognizant, which is a rather large software company, it turns out that having a graphical view of an overall system is actually very important for the top-level management. When they need to upgrade an old web service that's been there for 20 years that nobody actually knows what's going on in it at the moment, for the top-level management, if they get only measures in terms of number of lines of code or so, it doesn't really help them. They don't know exactly what that means in terms of complexity and money that they need to invest. Well, if we give them a graphical global point of view of that distributed system, then even though they might not understand the semantics behind it, they actually have a better idea of what is the complexity involved in that, the upgrade of that system. And on the theoretical side of our motivations, we have the multi-party session types framework, which was first introduced in this Purple 8 paper by Nobuko Yoshida, Kohei Honda, and Marco Carbone, where they basically advocate a process for developing distributed systems where you start from a choreography, so you start from a global view of the system to be. And if that choreography obeys some basic principles, it can be projected on each participant, so on each component of the distributed system. And later on, once the implementation has been done, so each component can be type checked, and those types are behavioral types. So they can be type checked against the processes. And if each component types check, then we have nice properties like deadlock freedom, all the messages that are sent are received, etc. And one obvious limitation of this framework is that it's very much unidirectional. So if you don't have the choreography from the start, then the whole process doesn't really apply. So what we're doing in this work is just reverse that arrow, so that from a set of local types, which in this work take the form of communicating finite state machines, we will build a choreography, which in this work is a global graph. So what are CFSMs? So communicating finite state machines were introduced quite a while ago. And it's a Turing-complete model. And it's a great model to reason about essentially interleaved TCP connections. So the idea is that you have several participants, could be more than two. And for each pair of participants, there are two channels, two buffers, one in each direction. So for instance, this buffer is for A to send messages to B, and this one is for B to send messages to A. And each automaton has a starting state, and all the transitions are labeled by either send action or receive action. So for instance, this transition says that A can send an apple to B, while this one says that B can receive an apple from A. And this model actually corresponds exactly to session types. So for instance, in this little example, A can send an apple, which is then buffered, and then can send an orange, buffered again. And then later on, it's an asynchronous model. B can receive the apple, then the orange. And because the buffers are unbounded, B can send as many oranges as it wants. And because, again, those buffers are unbounded, generally the number of states reachable from by a system of CFSM is infinite. So from these machines, we want to build a choreography, so a global representation of a set of CFSMs. As an example for this talk, I will use this little protocol that describes a very small game where there are 4 participants, Alice, Bob, Carol, and Dave. And the idea is that there is a choice where Alice chooses whether C wins the game or if B wins the game. If C wins the game, then C tells B that B has lost the game, and the other way around if B wins the game. Independently, so concurrently, there's an interaction between C and D. C tells D that she's busy. And so then the choice merges. Then there is another parallel behavior where B sends a signal to A and C sends a message to A concurrently, while there is a join here. Then there is another join, and A sends a message free to D. And then there is a recursive call, basically, so the game plays again. So this global graph, so this choreography, is actually obtained by our algorithm from these CFSMs. And I hope you agree with me that the meaning of the game is less clear on that side of the picture, or on that side. So for instance, the behavior of Carol is quite messy. So it's hard to see what is the purpose of those 4 machines, while in this picture it's much clearer. Right. So, yeah. So a few years ago, Malo Danielu and Nobuko Yoshida had this paper about projecting choreographies to CFSMs. And in this work, we are basically closing the loop. So we are characterizing from which CFSMs we can actually build a choreography. And we are giving the algorithm to build that choreography. And concretely, we have 2 goals. So one is to characterize what is to give a sound condition for safety for a set of CFSMs. So this condition can only be sound because the model is Turing complete, so we cannot have a complete characterization of safety in CFSM. So the idea is that we have this condition called generalized multi-party compatibility, which says that if S is GMC, then S is safe, so there is no deadlock and all the messages that are sent are received. And if S is GMC, then we can build a global graph such that if we project that global graph onto each participant, we obtain exactly the system we started from. So it means that the 2 specifications are equivalent up to projection. So a designer could modify or reason about G or about M, and that would be, or about S, that would be the same. Right, so how we do this? We start from the transition system of all the synchronous executions of the CFSMs. Then on this TS, we will check for safety. So we have a condition that ensures that we don't lose any information, and that if this holds, then we have safety. Then from this TS again, we can build a choreography by using the theory of regions and the one of Petri nets, self-Petri nets. So constructing this synchronous transition system is quite easy. The idea is that you just let the system execute with the additional constraint that a participant can only send a message if its partner is ready to receive it directly. So it's like executing it without buffers, just the synchronous semantics of CFSM. So in this example, if we let execute these 4 machines, we obtain synchronously, we obtain this LTS, which is always finite because there is a finite number of states here, so there is a finite number of states there because there is no buffers. So in a sense, this is already some kind of global specification because it actually contains all those machines. But we need to check whether we have actually enough information. And that's the first part of the check for safety. So we have this generalized multi-party compatibility condition, which has 2 subconditions. Representability, that ensures that TS has enough information. Again, in general, the state space is infinite, and the TS is finite, so we need to check that actually we have enough information to reason about this. And that check is pretty simple, actually. We can just project this TS onto each participant, so it becomes a non-deterministic automaton. And we can just check that it is branching bisimilar to the original machine for each participant. If this holds, then we know that we have information in that TS, and we can check that the interactions are well formed by using the branching property. That essentially for each branching the TS, so by branching I mean each node that has more than 2 outgoing edges, we check whether this branching is either corresponds to independent interactions, so it's a parallel, so it will commute a diamond, or it's a choice and it is well formed. And the typical conditions to check that it is well formed is that there is a unique participant making the decision. Because it's asynchronous, we need that only one participant decides which branch to follow. All the participants that are involved in that choice, so those participants that behave differently in the branches must receive a different message. So if these 2 conditions hold, then we know that the system, the CFSM, are safe. And from that point on, we can actually build that choreography. And for this, we use the work of Cortadella and others, which is based on the theory of regions. So the theory of regions, I think, first started in the late 80s, and essentially they gave a theory to derive a Petri-net from finite LTSs, so that Petri-net, the reachability graph of Petri-net is isomorphic to the initial LTS. And then Cortadella and others in '98 extended this work so that it can be applied to a bigger set of LTSs, also finite, and give you back a safe and extended free choice Petri-net, whose reachability graph is bisimilar to the original LTS. So we can use this theory basically as a black box, and we put in the TS, which is GMC, and we obtain a Petri-net like this. And this is already a bit more like the global graph I showed you initially. So we just have to make a few transformations that are possible because that Petri-net is safe. And so one of them is that we need the choreography to have a unique initial point, so a unique starting point. So for this, we take the initially marked places and join them with an initial transition. So now we have a unique starting point. Then we clean up a bit those crossing places there, so that we make actually join and merge apparent, so that these two places are basically, and two transitions are merged into this one. The idea is that those two places have the same preset. So this has close and close, and this as well. So we can just merge them with a silent transition. And then we can just basically do a few cleanup operations, and we then obtain the global graph we started, well, we actually wanted to have. And again, this is already much clearer than this. We have a prototype implementation of this algorithm that was positively evaluated by the Purple Artifact Committee this year. And it takes a textual representation of CFSMs, does the GMC check, and generates a picture that is then equivalent to the original CFSMs. Yeah, so just to sum up, I presented an effective way of checking whether CFSMs are safe. So it's a sound condition sufficient to check it. The algorithm is based on theory of regions, and it also gives you a CFSM characterization of graphical global types, graphical choreographies. And the tool is available here, and Emilio is actually working on a more user-friendly version of that tool. And recently, with Nobuko and Laura, who is here in the room as well, we extended this work to support communicating time automata, which are CFSMs that have time constraints on each transition. So messages need to be sent within deadlines. They must be also received in time. And this is to appear at Concur this year. And the draft is there. And I think that's all I had to do already, to say already. Yeah.
And then, okay, the thing you did was you kind of restricted your domain by requiring this synchronous graph, right? So you basically removed the use of buffers in your executions.
Well, the condition doesn't rely on buffers, yes. But then, so what it says is that if it's JMC, then any asynchronous execution will also be safe. So the condition is based on a synchronous product, but it doesn't restrict the execution in general.
What I was trying to ask is, do you have any, let's say, usable implementations in which you can specify using your CFSMs, like concurrent data structures, where you're able to, did you try any concurrent data structures in order to use camels without using CFSMs?
No, it's not really the kind of applications we're looking at. So we're more looking at abstract behavior of distributed system. It's a higher level in a sense. So for instance, at Cognizant have this zero deviation lifecycle venture that they have. They provide a service where they send their employees to, say, a large bank, and they extract some, say, UML-like specifications, so sequence diagrams, etc., of system. So they can easily, well, sort of easily, get those local specifications from given teams, but then combining them together is harder. So we are tackling more that kind of applications, yeah.
On that point, have you done any case studies or anything like that where you've taken actual examples of things that they've extracted, these UML things, and done this sort of choreography, putting them together from real life examples with the project partners?
Yeah, so in the paper, I actually didn't show that, but we've gone through 10, 15 use cases from literature, also from the BPM specification. And we always get something actually. Most of them, if not all of them, are GFC, except maybe one that we had to like swap two transitions to make it GMC. And the interesting thing is that the one from the BPMN specification, so we projected manually the BPMN choreography specification, fed it to the algorithm, and we got back exactly what the BPMN specification gave us. So yeah.
Can you say something on the size of this Cortadella construction? So what concerns me is the following. If you do this product, it will grow exponentially in the number of parallel components. And if you then, out of this big beast, make a patching net, it's still huge. Unless you tell me it's small.
So, okay, it's exponential if, if the parameter is a number of machines. But we tackled a fixed number of machines. So in terms, if you give me a fixed number of machines, then the size of the TS is polynomial.
In this parameter case.
Yeah. So if the parameter is the size of the CFSMs, then it's polynomial. But the theory of region is actually it is exponential in general. Yeah. So computing all the regions of an LTS is exponential.
Again, on this exponent.
Yeah. So the whole theory. But what they did in compared to the original theory in Cortadella's work is that so initially a region is defined in terms of set of states, while in Cortadella and others they have a condition on the set of events, which is very much smaller. So it's a bit more efficient, and actually they have you might know Petrify, a tool from '98 that actually works pretty well. So one of the biggest system we had at 12 machines, so that was producing something quite big already, around like 1,000 states, and the tool manages that in a few seconds, really.
And then the Petrinet has how many? So 2,000 states for the ATS, you say?
1,000, yeah, something like that. Then the Petrinet is very small because to generate those big protocols that are still kind of meaningful, what we did is that we take the parallel composition of several instances of that protocol. So for instance, if I take the running example and I have two parallel execution of that running example, like at 8 machines, and I get a much bigger graph because they're all interleaved, right? And then the Petrinet at the end is basically just twice that with a one transition at the top to create the parallelism, really.
So the region theory detects symmetries.
Oh, yeah, it really just so for the idea is that for each event, so each transition with the same label, there is one transition in the Petrinet. So it's rather small, really. Yeah.
So if you get the global distribution, global graph, and you project down these local graphs, then you try to do inference, what will you get back?
So if you so the idea is that if you start from S, so from a system of CFSMs, you get G. If you project again, then you will get the same up to some isomorphism. But if you start from G prime and you project this, then you will get something different, but which is equivalent up to projections.
Is it guaranteed that you get something back, or you might not be able to infer it?
Well, at the moment I have no proof that if this is well formed in the sense of previous papers, it is exactly GMC. It should be more or less that, but proving this would be tough. But yeah, the equivalence is up to projections. All right. Thanks.
So we have the first of many coffee breaks now. So we'll start again at 20 past with Uday's talk. Coffee's next.
Thank you very much.
Sorry?
Australia? Yeah.
So,
Sorry?
backslash color.
I think so.
Well, I would have had, I would have given you
So it should be big on
half the oil on yeah, I remember these places. Yeah, I saw the and there was
It's too
Yes.
It's nice to see.
Yeah. No, mine
they won't earn any money with that.
The only other service that I know that would really struggle is church. It's just game-based.
Why not?
And people will log in. Exactly. Well, people will log in and there will be Call of Duty or something bad.
Oh, so what? In YouTube you will log in and you get some, I don't know, some other stuff that's probably emulated.
If I knew in advance.
Yeah, I don't know, I didn't know you could. I never
So the completeness in the sense that we can.
I only noticed yesterday because the first thing I did here was get into a drum and then I had a drum line and I tried to think of
I think we had you do talk in succession.
Yeah.
So he came first and then you came 3 days later, a week later. And you were talking roughly similar things.
Yeah.
So that confused me.
But actually something we are doing now is try just did that. Well, like also in use of
There is
Oh, I have. I think it will last, but we just need to.
So a graphical choreography specified the equation system.
Okay, so I'm going to add color.
But I don't think also because we use the stereo vision, so I don't really know what I can do.
Yeah.
And over there, how do you do
What are you using to do that?
Well, I'm still using YouTube, but I'm using this cool program called OBS that pretty much does everything.
So it's just a camera plugged into there.
The camera is easy, it's
The
and the
mic
mics,
as well,
yeah,
put into the
just the
same
sound
thing.
card, yeah. Because Macs don't have audio in, so I need it together. Yeah. Well, I think it's really good.
I'm always keen to contrast things with Panopto because
It's not doing anything? Is it a mute and something?
Yeah, that should be working.
Check.
Is that working, Azalea?
Oh, it's only for the...
Yeah, it's working. Yeah, it's just for the YouTube.
All right.
Okay,
start?
So our next speaker is Uday Reddy from Birmingham.
Thank you, John. So this talk is joint with Claudio Hermida, who is somewhere in North or South America, and Edmund Robinson, who is in the audience. North or South because he is supposed to be resident in North, but he has been visiting his mother in South America. So we are the, I would like to call ourselves three musketeers, and our job is to carry the light of Reynolds's legacy. So after Reynolds passed away in 2012, we started thinking. I ended up giving several memorial talks on Reynolds's work, which kind of brought home to me the enormous power and range of Reynolds's ideas. So I've been thinking about that ever since. So that's what I'll start off with. So this is what I used to call parametricity theory, and many of you know it as parametricity. Now I call it Reynolds type theory, mainly because it gives a much better sense of what's actually going on. And I'll tell you later on how this perspective is probably more useful than just parametricity. So the intuitions of Reynolds type theory go long way back, and I would like to connect it to Felix Klein's Erlangen program. And the idea of Klein was that, this is my way of paraphrasing, explaining, he didn't use these words, but whenever you define any kind of mathematical concept, you're forced to incorporate some essential information and some inessential information. And this inessential information doesn't matter to the theory, so you can kind of change it. And changing the inessential information is what comes out as what mathematicians call symmetries. For us, symmetries are much more fancy than they happen in mathematics. They give rise to information hiding, data abstraction, equivalences, observational equivalences, and so on. But the principle is still very much the same. So what are symmetries? They are differences that you can make to the basic data that cannot be observed within the theory. And so they give rise to observational equivalences. Reynolds's idea was that you could get hold of this kind of analysis just by looking at the types. So types were very crucial for Reynolds. And if you have the right type, then the right symmetries fall out of it, and they give you the right kind of equivalences. If you don't get the right equivalences, that means your type was wrong, and you have to go back and fix the type. You have to change it. And we'll see later on several examples of how you can change types, which completely give rise to different symmetries. So the types are everything. And if you look at Reynolds's work from, say, 1980 onwards, you will see this thread kind of going through in everything he did. So during Klein and Poincaré times, Poincaré actually did a lot of the stuff Klein wanted to do. So he ended up doing what Klein proposed as the Erlangen program. But without Klein, we would not have understood the impact of what Poincaré did either. So it's a good idea to keep them together. So in their times, the symmetries were isomorphisms. For us, symmetries are going to be logical relations. And the difference is that isomorphisms are one-to-one correspondences. Logical relations are many-to-many correspondences. They're relations. And the reason we need many-to-many is because we have more information hiding in computer science phenomena than they do in mathematics. But relations go back all the way to Turing. So in Turing's PhD thesis, he was talking about virtual types, which are partial equivalence relations. And from our point of view, the first big computer science application of relations was in automata theory, which and they called them generalized homomorphisms. And Milner renamed them to simulation relations, and we all know currently by simulation. The second term, logical relation, was coined by Mike Gordon and Gordon Plotkin. And Mike Gordon knew some of the stuff coming down from Tarski, etc., and that's probably how the term logical came into picture there. but there's not really much logic. So whenever you hear logical relation, think of it as a structure preserving relation. Just like homomorphisms are structure preserving mappings, logical relations are structure preserving relations. So combining all the intuitions we got from all this bunch of work, we wrote a Reynolds memorial paper where we propose this thing called Reynolds program, which is to apply these ideas to almost all the phenomena that we know in category theory and programming languages. That's what I thought about at that time. But nowadays, I think that it's also applicable to broader mathematics. Topology is something that I'm looking at now, which seems to be very applicable in this context. So in the general sense, so we can think about type theories in three levels. Set theory is the most basic type theory, where you just have types. Category theory is the next level, where you, in addition to types, you have morphisms, which bring out the structure of the types. In Reynolds type theory, you have yet another new component, the relations. So people who know category theory know that when you go from set theory to category theory, things that are the same concept can split into different concepts. So complete lattices and complete semi-lattices are the same things as sets, but once you look at morphisms, the difference between them becomes apparent. Similar thing happens again when we add relations. Things that are the same in category theory, and here is an example, become distinct when you consider relations. So this kind of stuff will go on when we look at process algebra. So the objective of this work is to apply these ideas to study concurrent processes. We don't have concurrency yet in our theory, but processes is what we will focus on today. So the inessential information in processes is in terms of states, because states are hidden, they cannot be seen by the external observer, and therefore changing the state, applying relations to states, will give us differences that the theory cannot observe, or at least the computation cannot observe. So whenever I say symmetry, I mean, I won't use it a whole lot. Just think of it as a change that cannot be observed. So here is a simple picture through which you can think about all these ideas. So two types, A and A prime, and they have some difference between them, which we believe cannot be observed in the theory. And that difference can be captured by a binary relation between them. And any operation you have in the theory should be such that if you change things by that difference in the arguments, the results should again have exactly the same difference. So this is the basic picture of relational parametricity. This family of functions T, which is indexed by types A here, is parametric if related things map to related things. And there it is in words, but it's just what I just explained. Okay, how are we doing on time? I can't see my time clock here. Okay, so now let's get to processes. Now, I come from programming language theory, and I don't know a whole lot about processes, but here are the main things that I realize are different. The very first thing is that processes are reactive. They do things one step at a time, and we can observe what they're doing. We cannot observe the states, but we can observe what they're doing. They're almost always non-deterministic. And here is the thing that is irritating to me as a programming language theorist, is that there is no agreement on what is observable from a process. So there are different notions of what is observable, which give rise to different equivalences, and there is a whole lot of debate about what they mean. So here are three equivalences that I'll focus on today. It's really the testing equivalence which is the most interesting one, and these two are kind of warm-up exercises before we go to the testing. So trace equivalence, they say, two processes, if they may accept the same traces, they are considered trace equivalent. By similarity, which is probably the best known process equivalence, it says that processes maintain equivalence at every step. If you have two equivalent states, after doing the same step, they should again go to equivalence states. Testing equivalence, again, this is using a traditional description. says that two processes are equivalent if they pass the same tests. Let's look at an example of the three. Do I need to explain what these notations mean, or everybody knows? Well, this is a concurrency workshop. All right. So these three processes are identified in trace equivalence. Why? Because, well, let me show the next bits also. Why? Because all three of them basically accept ABC as well as ABD. By similarity, it distinguishes all three. It says all three are different, but it's hard to see how they are different unless you are a bisimilarity guy. But testing equivalence, which seems a bit more understandable, it says that X is different from Y and Z, but Y and Z are the same. So let's think about the difference between X and Y. Now, in this process, after doing A and B, we're in a state where we can do either C or D, well, both C or D, whereas here, the C has the possibility of acceptance here, and C does not work if we happen to be in that state. So the difference between X and Y is clear, but is the difference between Y and Z clear? What does it mean for Y and Z to be different? So there's a whole lot of lingo that concurrency theorists use, like may equivalence or may testing and must testing, linear time and branching time, and reactive versus transformational. For me, as a programming language theorist, none of it really explains what's going on. So let's see what we can do. So we want to talk about effects. So there are effects going on, during process execution, which have to do with undefinedness. You might try to do an operation which doesn't work, or you have non-determinism. There are several possible results a process might give. So there are two effects that are inherent in process notions. The second important thing here is that in normal programming languages, these effects are observable only at the top level. So you run a program, and when the program finishes, you get to see whether it has diverged or whether it has given one of possible several results. Whereas in reactive systems, this is a fundamental difference for me as coming from a programming language point of view, is that these effects are also observable at intermediate steps. So going back to the picture, oh, maybe that picture repeats. So we can observe divergence at every step. So after doing an A and a B, I might try to do a D here, and that will be undefined, that diverges. So I don't have to wait until I finish the whole thing in order to see whether a divergence has occurred. The divergence may occur at an intermediate point, and I can observe it. So this seems to be the first difference that we need to capture. And the second thing is that non-determinism also, at least some people believe, is observable at intermediate steps. So the difference between Y and Z is that the branching point here occurs after A. There it occurs initially. Now we cannot really see from the outside where that choice point has been made, but we can imagine that we can see somehow that a branching happened inside the system. So some people also talk about it as a branching time. For me, actually, a better explanation is in terms of snapback. So after I have gotten a hold of that state, maybe I can fix that state and go back and try several experiments. And here I see that sometimes BC works and sometimes BD works, whereas if I was here, I know that only BC works, BD never works. So snapback is another way of understanding the effect occurrence that's going on there. So we can now explain the difference between the three equivalences using the effects and when we observe the effects. Trace equivalence says that both the effects, divergence and non-determinism, are only observable for entire runs. They're not observable at intermediate points. Bisimilarity is saying that divergence and non-determinism are both observable at every intermediate point. Testing equivalence is saying that divergence is only observable at intermediate steps. Sorry, divergence is observable at intermediate steps, but non-determinism is only observable for the entire run. Okay, is that distinction clear? So coming back, the divergence, the fact that D is not defined here, is observable in testing. But the fact that the non-determinism, internal non-determinism is different, well, it's not observable at all, because you're only going to see at the end whether all the branches have been possible. Okay. I'll have to rush through stuff quite a bit, but I'll explain the basic theory. Right. So programming language theorists would also know that effects are captured in type theory using monads. So a monad is an endofunctor, a functor from a category to itself, which has these two operations, unit and multiplication. Now, in call by value languages, monads capture the effects by saying that, well, if I have one computation which has an effect and another one after it which has another effect perhaps, then we can use the T functor, since it's an endofunctor, to lift this second computation to the next level. Then we can compose them, and then we can use the multiplier to collapse these two things. So now I want to think about this operationally. This T says there is an effect, maybe a divergence, maybe a non-deterministic choice. And this TT says that there are two effects that have been cascaded. And this mu says I'm going to collapse those two effects into one. So this kind of composition captures how effects are observable for entire runs. For reactive systems, we're never going to collapse anything. So I drew this in blue. So these are all things that are happening overall. And so we can, the end result will tell us if an effect has happened, at which step it has happened. So I wish I had a similar explanation of all the three equivalences, but I don't. Okay, so the monads we will need for our effects are divergence, which allows results to be either undefined or defined, and what I call real non-determinism, that is without any divergence, so non-empty subsets, and combined non-determinism, which combines both of these. I'll skip that. Now, I'll skip the behavior parts, but I'll show you the types, which is all that we have time for. Okay, so here's the label transition system, which has a set of states and a bunch of transition relations. Now we're going to think about how to write a type for that. You know, what is the type of the transition relation? There are various possibilities, right? It's a subset of the product, or it's a function from A to another relation, etc., etc. All of these are identical, or they're isomorphic in set theory. Many of them are also isomorphic in category theory, but in Reynolds type theory, where we think of relations as symmetries, almost all of them are different. Okay, so we need to look at what's happening and produce the right type. I'll skip this also. So I'll show you three types: the type that is needed for bisimilarity, the type that's needed for trace equivalence, and the type for testing equivalence. So for bisimilarity, we use the most basic type, which is that the transition function takes an input symbol, and for an initial state, it gives a bunch of possible output states. And if you work out what the logical relations for that type are, we get bisimulation. for testing, for traces, remember we said that the effects are observable only for the entire run. They are not observable at the intermediate points. And that requires us to think about functions from, let's see, functions from, well, earlier we had functions from the states to set of states. Now, any such function can also be thought about as an additive function. That is a function that preserves all the unions from the power set of states to power set of states. So, this lollipop means additive function. It's kind of the algebra homomorphism here. And the relations are then defined to preserve that. And if we work out what that means, that means stuff similar to what automata theorists do in order to do state minimization or state equivalence. So, you have relations between sets of states instead of individual states. Okay. Now, I have 3 minutes. Okay. So, testing is the hardest one. Why? Because we have two effects going on, divergence and non-determinism. And divergence is observable at every step, but non-determinism is only observable for the entire run. So, we have to separate this P monad, the power set monad, into two parts, allow one of them to be observable immediately, and let the second one be cascaded until we get to the end of the run. So, after searching for quite a bit, here is the type constructor that we need. So, I wrote it as P2, which is equivalent to this composite. And so, P2 of x has three possible kinds of values. The first one says that this is a computation that has definitely diverged. And the second one says the computation that has a defined result. And the third one says, well, it may be undefined or it has a defined result. So, three possibilities that exist for P2. And this P2 has some nice categorical structure, which allows it to work with the non-empty power set monad, with the real non-determinism monad. And the effect of that is that we can then write the type of the transition function as this. So, note that the non-determinism is observable only for the entire run. So, this is similar to what we did at the trace equivalence for the trace equivalence. But divergence is observable at each step. So, this is similar to what we did for bisimilarity. So, we are combining these two ideas now, and that gives us a new notion of a new type, and from that a new notion of symmetry and a notion of logical relations for that. So, here are the three examples and the three processes, and here is what the testing equivalence type tells us. So, for the x machine, if we start from this set of initial states, then I terminate and I get this set of initial next states. Then for the next step again we terminate, and for the third step also we terminate. If I do the y machine, then everything runs similar up to here, but here when I do b in this state, I get a set of two states. So, I could be in either one of these. And then if I do c in this, starting from 2 1 I get 3 1, but starting from 2 2 doing c will give me undefined. So, we get that result. If we calculate what happens for the z machine, we also get the same result. Okay, so, the logical relation here tells us that these two processes have exactly the same behavior. Okay, so, in conclusion, what we have is a notion of type theory which captures the observable behavior, and from that derives the notions of equivalence that are of interest to process theorists. And the relations we get from logical relations and parametricity match up with what we are familiar with from process algebra. But we don't have process algebra yet. There is no concurrency. I only talked about label transition systems. And the reason I'm not talking about concurrency yet is that concurrency involves silent transitions. which I anticipate will be a major challenge for the type theoretic point of view. Why? Because silent transitions are invisible, so they should be hidden, they should disappear. However, they do make a difference. Once you combine silent transitions with non-determinism, we know that we cannot eliminate them. Whether they are there or not makes a big difference. And therefore, I am giving myself enough time to, to think about that. My co-authors, Edmund and Claudio, do have some ideas, but I'm not yet convinced that we have the answers yet. So there's a lot that needs to be done about it. And the whole notion of reactivity and how that is being captured by monads, I think, is also quite interesting. And hopefully, more people will think about it and develop more theory. Thank you.
So is Carlo here? Would you like to start setting up while we take? I think we just have time for maybe a couple of questions for you.
I closed my machine.
Does the different states that you get in those traces, does it relate to having a sub-affecting, different kinds of sub-affecting in the branches, the different types that you show, different process types? Does that come into it? Are you sort of looking at the branches and the effects that they raise, and then sort of they're combining to understand about?
Yeah, there's no clear notion of a sub-effect here. And some effects can be combined and some cannot. In this case, it's easy to combine divergence and non-determinism. And power set monad is something that we think is most natural thing to use. And it turns out power set monad can be split into those two.
The branching is in the power set rather than in some actual different branches in the computation.
Yeah. But operationally, I don't think power set monad is natural at all. I mean, it's a very strange thing. Why should you be combining non-determinism and divergence in that way, as if they don't matter, as if it's all the same thing? So the power set monad, in mathematics, it's, in set theory, it's a perfectly fine thing, but operationally, it's a very strange thing. So that's why I call the non-determinism one the real non-determinism. Adding empty set there is a strange thing to do. But just combining it the traditional way doesn't give us what we want. So we had to do much harder. We had to work much harder to produce that P2 functor that I showed you. And I don't think P2 is a monad. It's a functor, and that's enough. That's all that's needed, because P2 is never cascaded. It's carried around. So what? That's right. You build up a tower of P2s, and that's all you need. Yeah.
So I just had one question. So you had these three notions of equivalence, and one of them you could observe divergence and non-determinism at the start. One of them you could observe both at any point, and this third one you could observe one at the start and one at any point.
Yeah.
And I was just wondering, it seemed to be a natural fourth that where you could observe divergence only at the start and then non-determinism at any point. The missing one in the 2x2 grid, does that give rise to an interesting notion of equivalence as well?
Possibly, and I think working out the type is going to be much harder because testing itself was much harder. But I don't know what it means to observe non-determinism in the middle. It's a very mystical notion. I think, I mean, I don't know, there are many CCS calculus people here. I don't know how they understand it. I'd like to talk to them and find out. I mean, maybe they use it just because it's a nice, convenient, elegant theoretical device. And it's not really the equivalence they care about, but it happens to be useful practically. How many more questions do you want me to take?
Well, are you ready? Oh, you haven't? Yeah. Okay. So maybe we could keep doing some questions more.
Okay, let me take.
The type theory development is very semantic, but there are, as you know, lots of types of type theories, and they're typically using the idea of channel rather than the process. So how do you expect to integrate these two approaches to type theories?
Okay, so syntax. So I mean, if you read the introduction of Reynolds' types abstraction parametric polymorphism paper, he's telling us what is the semantic thing we care about and how the syntax helps us to get there. So he's telling us that types are about enforcing levels of abstraction, and type systems enforce it for us. So type checkers make sure that we don't violate the levels of abstraction. So if we just have a syntactic system, you have a bunch of rules, but do you really know what it is enforcing? So you want to think about the levels of abstraction that you're trying to protect. So for that reason, I would encourage you to think about the semantics behind the syntactic systems as well. Okay?
Thanks,
Okay.
Uday.
All right. Thanks.
Can you grab your microphone?
Yep.
Questions, could you repeat them so that everyone can hear?
Okay. Okay, hi. I'm Carlo. I'm going to present a method to infer session types automatically from ML code. And this is going to work with Vasilius, who is in the audience here. So just as a reminder, in case some people are not familiar with session types, a session type guarantees that the interactions at the two ends of an endpoint always follow some protocol. So if one endpoint, there is a send happening on one protocol or one end of the channel, the other channel will be expecting to receive some value, and hopefully of the same type. The idea is from the 90s, from the work of Koei Honda, and from there, there's been a lot of research. The session types community is very active, and we have multi-party session types, contracts, extra guarantees like deadlock freedom, and embeddings of session types in functional languages, which is where this work is going. So we have taken ML with the standard sequential features of ML, such as lambda abstractions, let expressions, if and else, so nothing new there. And we have added session primitives, like a spawn primitive for concurrency, which has the effect of spawning a new process, a request and an accept primitive that instantiate a new connection between two processes. So we assume that we have a list of global channels. You can think of them as URLs. And each, the S and the S prime are freshly generated endpoints, which are private to P1 and P2. The operations that are allowed on these channels are sending and receiving a value over the endpoints. And we expect the session types to have this kind of protocol where VS type T. So the value sent over, and the protocols are respected. The protocol can offer a number of choices of options, and P1 can ask P2 to play up to a role, let's say, a role L, which is again a fixed constant. And through the match construct, P2 will agree to perform that role. And finally, there is a possibility to delegate endpoints. So if you imagine to have this configuration, P1 can send his own endpoint, S1, to P2, and the connection is switched over to P2. So let's look at some examples. This is the standard swap channel. We have two P1 and P2 that want to exchange their own values. And we have two functions, doSwap and doSwap prime. They start a connection on this general swap channel. And they simply send and receive their own values. So this is very simple. Of course, this is not a good solution in general. It's not a symmetric function. We would like to have a symmetric swap. So as an advancement, we can provide a swap service that works through a coordinator C. The coordinator opens a channel with one partner they want to swap and manages the swapping. So P1 sends its own value to C, P2 connects to the coordinator, it sends the value, and C performs the swap. Again, imagine if you're trying to exchange big data, such as a movie or an MP3 file. You don't want the coordinator to be the bottleneck of the system. So a new upgrade of the swap service will be the peer-to-peer swap service, where basically the coordinator doesn't do the swapping of values. It just assigns roles to P1 and P2. So P1 will be the server in the swap. P2 will be the client. And then it delegates its connection. And now the swap can happen as in the first case. So our goal is to, given this ML language with session communications, is to have a fully automatic inference of session types with no annotations, so no help from the programmer. And of course, we would like to have some type guarantees, such as session type guarantees, that the protocol is always followed, but also some deadlock freedom guarantee. For example, that there are no circular weights. And we show that under some conditions, this is possible in this language. And the challenge is, of course, we have the code complexity. It's a functional language, so there are functional calls. There is delegation, which is not trivial to treat. And aliasing of endpoints is a big problem because of assignment of variables. And as yet, it's still not clear how to do inference with no annotations. And of course, we would like to have a conservative extension of ML. So whatever is typed in the pure ML is also typable here. And we will also like to have an approach that is scalable to other features, such as references, exceptions, etc. So this is the framework for type checking. Given the ML code with some type, fundamentally an ML type, we require the type checking, the program type checks if two things are provided. A process algebra behavior, so a process algebra whose whose concurrent effects simulate the concurrent effects of the ML code. So if the ML code sends a value, the process algebra also has a send. And the second thing we have to provide for the type checking is, of course, the session types. And the session type is the type discipline is checked on the process algebra. And because of this simulation property, if the process algebra type checks with reference to the session types, then also the ML code type checks. And our type discipline is inspired by Castagna, which provides a form of deadlock freedom. And now, if we go to the inference, so we start with the ML code. We want to find, of course, the process algebra first. So we use there is an approximation step with value flow and control flow analysis, which we will explain. The session type inference is performed on the process algebra. And of course, it's much simpler to perform inference there. And the inference is performed locally for each process that is spawned in the ML code. And finally, we compose back all the local views of the session types into a global session type. So if we start with the peer-to-peer swap, the first thing we want to approximate the endpoints. So endpoints are dynamic entities. We want to have a static view of endpoints. And we use a well-known technique known as region analysis. So if you see here, resume, accept, request are all sources of endpoints in the code. So we have 4 syntactic occurrences of primitives that generate endpoints. And these are the variable assignments that are affected by these sources. So we assign a unique label to each syntactic occurrence of each of these primitives. and we assign a region to each variable. And region analysis tells us which endpoints flow into which region. And in our framework, we require that there is exactly one label flowing in each region. And this takes care of aliasing. So it's always clear which endpoint is going where in the code. So this is the first step in the approximation. And then we want to get the behavior. We want to get the actual process. And we use well-known techniques, which is the type and effect system from Nielsen and Nielsen. We adapt it from CML to MLS, ML with sessions. And we get this process here for the swap function that generates a new endpoint, L1, which is the static one, with some session type swap. And then it offers two choices. And there is this other process algebra-like term that type T1 is sent over L1, type T2 is sent over L2, is received from L1, and the protocol is finished. And the coordinator creates two new sessions on L3 and L4 with the same type. If you remember, it's the accepts are on both the same swap global channel. And then there is a delegation here and a recursive call. So we go to the second step of the inference. We define an abstract interpretation semantics for these process algebras, which gives rise to an LTS of this kind. And the idea is that a process is well typed if it follows the session type throughout all the paths that it defines. The inference, of course, just explores all the paths. It's not trivial. It's not easy to understand when to close an endpoint, or there is some subtyping going on when discovering branches. And the important point is that these LTSs are all finite. So we include some restrictions in the language. We try to have recursive behaviors, for example, with finite sessions. We allow recursive communications, but that are finite in nature. This is what we're going to show in this talk, but there are also ways of extending this approach to recursive session types, which are not presented here. And since we do this inference on each process, the inference is proportional to the code, more or less, and there is no state explosion. And this is the inferred session type by this exploration. And now for recursive behaviors, such as the coordinator, for decidability, it's important to have a finite LTS. So the restriction that I mentioned is that the recursive behaviors are self-contained. That is, endpoints are always scoped within a loop of recursive behavior, and endpoints cannot be passed to the recursive function. So all the endpoints are local to a single pass of a loop. So basically, we can forget about this recursive call. And the inference again explores the path, and because of this delegation here, the inference locally cannot infer what the session type of L2 is. And so combining the information we have gathered so far, in the last step, which is the duality check, we're able to discover that S2 has this form, basically thanks to the session type that we discovered previously. And there are also other constraints on subtyping that we can discover. And for example, that the swap works with polymorphism. Works with subtyping. So if we imagine channels exchanging circles and squares, which are subtypes of shapes, the swap function can send a square and receive a shape, basically. And because of a property of this composition is that well-type processes are weakly deadlock-free. So in a functional language, we cannot rule out divergence. And another condition on the number of available partners on the global channels. But if a system doesn't have divergence and doesn't have, and this other condition is satisfied, which are both undecidable conditions, then the system is guaranteed to converge. So all sessions are finished, and there is no circular. There are no circular weights, and there are no deadlocks. And so this is the conclusion. So we presented a method to add session communications to ML. The inference is sound and complete. There is no annotation required from the programmer, and the types are inferred automatically, and there are some extra type safety guarantees, such as deadlock freedom. And we're currently implementing a prototype on top of the OCaml compiler. So I'm finished.
Any questions for Carlo? I'm not sure if the question makes sense, but you said you'd like the approach to scale up with the ML features, in particular to handle state and exceptions and this kind of thing. So the original ML type system has to be careful with these features. Does that apply also to your work with session types? Could you repeat the question?
Yeah, so the question is that you have to be careful when extending this work with ML features such as state and exceptions. Yeah, it's not immediate. For example, for exceptions, you have to include some exception mechanism in the behavior that you extract. So there is some modification that has to occur. But it's a possible modification. It's a feasible or feasible extension to the work. Yeah. No, I didn't go into the. Oh, sorry. So the question is, how do you deal with higher order functions being sent over channels and channels being sent over? So I didn't go into the details, but basically you can request that this self-contained restriction also applies to functions. And is there a marker? So in this, sorry. So in this framework, we sorry. So in these frameworks, functions have also effects. So a function of type T1 to T2 is also associated to behavior bit, which is the behavior of the body of the function. So you can basically request that this behavior is also self-contained. So if it's self-contained, then there is no problem in sending around higher order functions or channels. Pardon? Sure. Yeah.
So going back to the previous question, you must have to deal with the value restriction already, since channels. I mean, certainly in other message passing MLs, you can encode references using channels without, very straightforwardly. So.
Yeah. So okay, the question is how does it work with polymorphism?
Right.
Yeah. So basically, the work from Nielsen and Nielsen calculate the dangerous variables that cannot be generalized So there is no value restriction in their work. And basically, you cannot generalize variables which occur in effects that have already taken place. So if I've instantiated a new session with some session type, and the polymorphism, the generalization occurs after that, they have a way of calculating that that session type variables cannot be generalized. So there is a bit of machinery going on there. But they prove that their algorithm is sound and complete with their kind of polymorphism.
But is it more general than the value restriction? I mean, is it that they type more programs that way?
I would guess so, but it's a good question.
Presumably.
Yeah, presumably it would be, yeah.
Cool. Okay.
Thanks.
So there's another 20-minute coffee break now, and we can recommence at 3:30. Windsor from University of York, who will be verifying a single producer stack before our very eyes.
Okay, am I ready to start? Okay. Hi, I'm Matt Windsor. I'm from the University of York. My supervisor will be actually in the next session talking about something completely different, so that's going to be interesting to watch. I, on the other hand, will be talking indeed about verifying a single producer stack. So the first question, the first order of the day would be, well, what stack am I wanting to verify, and why is it interesting as an example for verification? So I'm going to be looking at the SP pool, which is a small part of the timestamp stack by Mike Dodds, Andreas Haas, and Christoph Kirsch that they were talking about in a paper in Popple 15. So this is just a small part of it, but it's interesting for reasons I will come to in just a bit. So the first order of the day is what you might expect from a stack. It has nodes. They go down in what looks like a linked list for the time being. There is a top pointer, and there's also this kind of interesting idea of having a node being taken or non-taken whilst still being part of the linked list. So I'll come back to the significance of that in just a bit. How do we know we've got to the end of the list? Well, there's a sentinel node which loops back onto itself with its next pointer. It's the only node that's allowed to do that, so we can easily just check, have we reached a node that points to itself? And it's a single producer pool, which means that I've said push threads here. In actual fact, there can only be one push thread, and pushing is fairly simple as a result because there's no contention. I don't know if you can see that. So there's a node being created non-atomically in thread local memory, and then we have this atomic assignment. We're assuming here that all assignments are atomic, sequential consistency, all that good stuff, which just swaps the new node in as the new top. We have a single producer data structure. We can do that. There won't be any races between insert and insert. We also have multiple pop threads. It wouldn't be a concurrent stack without them. And popping in the SP pool is slightly more challenging. We have this non-atomic traversal of the SP pool all the way down to, from the top as it was when we started, to the youngest node. And what we mean by the youngest node is the first one we see that isn't taken. So what we do after that is we try and remove it, and that is a compare and swap on the taken flag. We're just marking it as taken, and if it isn't already marked as such, we can remove it. So that is just a simple compare and swap, and then some more stuff I'll get onto in quite literally the next slide. So you may have noticed that we're inserting nodes. We're physically inserting nodes into the pool, and our pop isn't physically removing them, it's just marking them as taken, which means we can go to a state where abstractly we have A, and then following it we have E. In the concrete world, we actually have any number of taken nodes between the two, and our while loops have to go down them, saying, oh, you taken, oh, you taken, oh, you taken, oh, you're not taken. So that wastes time, it also wastes space, it also means we'll eventually run out of memory. So how can we fix this whilst keeping the same algorithm? Well, what we can do is we can say, look, everything between A and E is taken. Why don't we move A's next pointer so that it points to E instead? And what that does is it just takes these taken nodes out of what we call the spine, which is the area between the top node and the sentinel node. And the main way we do this is by something I call forwards compression, because we're moving forwards from A, kind of moving down non-atomically in a while loop. Have we reached a non-taken node? If we have, then we can just atomically reassign the next pointer. And the result is as follows. everything after A is moved off the spine. So great, we've got rid of it, hopefully. We also have another thing called backwards compression, which is whenever we're doing a pop, we can assert, because we've done this traversal from the top all the way down to the first non-taken node, things don't get moved back from takenness to non-takenness. So as long as we've still got that top being the actual top of the data structure, which is what the compare and swap is doing in part, we can say, right, top pointer can move down to what was the youngest node, and we've got some more taken nodes removed. We're assuming that we have some way of preventing the ABA problem here, because otherwise this wouldn't be, we wouldn't be allowed to do this. So we're going to reach some complexity here, which is why I'm talking about this stack to you right now. I wouldn't be doing so if it was a simple stack 5-day proof. So compression takes our lovely linked list from top to Sentinel, and it does this to it. We've moved all the kind of taken nodes, or some of the taken nodes, sorry, out of the spine, which, as we've said previously, that's good, right? We've got rid of them. If we have garbage collection, we can just remove these outlying nodes completely and just send up the linked list. So the sad truth of the fact is we actually have these non-atomic while loop traversals moving down. At any point when we're doing compression, those could be sitting on one of the nodes that swept out. So what was just a normal traversal moving down from top to Sentinel on the left-hand side has become this rather strange thing where we're moving down, being shunted off, moving back in, being shunted off, moving back in. And the first thing we want to know is, does this introduce any horrible data races? So if we take compression in parallel with itself, what do we get? So here's an example of what can happen. Say we've got this SP pool with 3 nodes, A, B, and C, maybe something in between each. Everything between A and B and between B and C is taken. So what we'd expect if we did a forwards compression from A now, we would expect it to move down to B, where that blue arrow is pointing, which is great. But then suppose we have a context switch to another thread which decides it wants to remove B, and it does so by marking it's taken. So now everything from A to C is taken, right? What happens if we do another compression, and because of compression being done at insert and remove, a node can be compressed from forwards compressed from twice. This is the second one. It moves past B, and now it hits C. So we've got these 2 compressions that have been sort of suspended. They've done their while loop, but they haven't done their assignment. What happens if we take one before the other, or if we take them in the reverse order? So if we take the longest one first, we have this situation where everything after A is being moved off the spine. It's now grayed out. It's not visible to the sort of main algorithm anymore. But then what happens if we do the next compression? Well, we've seen nodes almost rise from the grave. They've gone back onto the pool, and this kind of behavior where we're losing nodes, regaining them, losing them, regaining them, it's obviously a data race, and it's quite difficult to reason about. So what we want to do, obviously, is we want to show that, yes, it's chaotic, things are moving in and out of our pool, but it really doesn't matter. We actually can show some invariants, like there being no cycles, everything. The main thing we want to show really is we don't lose any nodes. So everything that's non-taken is on the spine and is always on the spine. It's only the taken nodes that get moved around, and only in ways that make sense. So really what we want to do is formally prove these properties hold. And the way I went about it was using a program logic called ICAP, which is Impredicative Concurrent Abstract Predicates. It's quite nice higher order concurrent separation logic. Now, you're probably wondering, why am I using a higher order logic? This isn't inherently higher order. The reason is because it treats abstraction in quite a nice way. We have this idea that we can model the abstract state of the SP pool as this labeled transition system, which kind of induces a protocol on how threads use shared state. And as I'm going to show, this works well to a point, and we'll see areas where it doesn't work as well as we might want. So the abstract shape of the SP pool, probably you wouldn't expect it to look like a 6-tuple of nodes and sets of nodes, but that's the way that I've been looking at it because it makes things quite easy for reasons we'll see later. These actually entirely characterize the SP pool for what we want. Some of them are actually ghost state, so there are things in there that don't actually happen in the concrete state directly, but we need them to be able to reason about memory safety. And I'm just going to walk through all the things we've got. We've got the set of non-taken nodes, so in this diagram there's only A that's non-taken, so the set would just be A. We also have a set of taken nodes, so we have all the nodes in the pool split into 2 disjoint sets. This also includes the nodes that have been swept off, so as you can see, C has also been put in that set. We have the top and sentinel nodes, so we know where the spine is because it's characterized as the nodes between the two. We also have the set of physical pointers, so pairs of node and then another node that it has a next pointer to, and we can get a physical order by closing over that. And then the bit of ghost state we need for this proof is this idea of a temporal pointer, which is created when one node is inserted. We record the node and the top, what was the top before it was inserted. So without compression, the two would be identical. The only reason anything has a next pointer to something that wasn't its previous top is if we've compressed. So we can take the reflexive transitive closure of both of those and we get 2 orders. So we've got sets and orders. This isn't sounding very separation logic-y, I'll admit. So what we also have, obviously, are these labeled transitions, and we have one for every atomic action that actually affects the state of shared memory. So we have popping, pushing, and the 2 compressions. As you can see, all of them affect different parts of the shared state. What we want to do is have transitions that are general enough that we can capture this very racy algorithm, but not so general that we start admitting things that aren't even possible in the algorithm. And well, I have an example from the sort of forwards compression end of things. So compression actually looks like this when we generalize it enough to admit the compression data race. What we've done is shown that we can actually have a B and a C here that are on 2 different branches, whereas we might have originally thought that compression just swings downwards. So that's surprising, but it actually works. And what we want to know is we've got this kind of graphical model of compression, so how does ICAP capture that formally? And the result is something that looks a bit like this, which is 6-tuple on one side, some conditions that are required for this to be for this to go through properly, such as all the nodes kind of below the previous target of the pointer, the next target of the pointer, up until they join back into one branch, they all have to be taken. Otherwise, we could lose non-taken nodes, we could gain non-taken nodes. As you can see, what we actually have is just a pointer update, but the transition relation here is talking about the whole set, the whole state of the SP pool. there's no framing, there's no separation. We can't say we're only looking at this and everything else is invariant, which is one of the drawbacks of using a logic like ICAP. And it doesn't make the proof impossible, it just means that we have to reason about lots of things that we don't want to. So how am I defining this all taken property, and how am I showing that this compression can't do things like move upwards instead of downwards and create cycles and destroy the consistency of the pool? So we use this idea of temporal order, which is our ghost state. We can actually order every single node with respect to every other node because there's a single producer. So there is a total order on insertion. And that means we can do things like say, well, everything between B and the meet point in terms of orders, so everything ordered between those two is taken. And that's much easier than trying to do gymnastics with all sorts of partial ordering. And the other thing is we maintain this property that the physical order is always a subset of the insertion order. So if we've ever changed a pointer, it's always to something that is it's always to some sort of transitive walk down of pointers, which makes sense intuitively when you think about the algorithm. But that allows us to say we've never moved something in such a way that creates a cycle. And we want to be able to show that anything that's changed the physical order from the insertion order only concerns taken nodes. So as far as the algorithm, the SP pool is concerned, nothing has happened because it always ignores those taken nodes anyway. So what are my conclusions from doing this? And I realise I haven't really talked, I've only been able to give a brief insight into what I've been doing. So I believe that we're correct in saying that this pool is memory safe. There's quite a list of properties that it adheres to. The only caveat there is that I haven't fully finished a formal proof. I've got something in ICAP that looks good, but it still needs to be kind of run through more experienced eyes and fixed up, because I've only been doing this for about 9 or so months. As far as linearizability goes, so actual correctness, is this a linearizable stack? Is it a correct stack? We don't have as conclusive a story just yet. I've been just looking at this kind of recently, and it looks like using the stack theorem that Dodds, Haas, and Kirsch used to prove the whole timestamp stack linearizable is the best way to go about this. I'm not sure how to massage it into an ICAP-friendly format, and I haven't yet been able to formally show that we have LIFO order, which is obviously what we want from a stack. In terms of linearizability to something easier, to a set, all of the memory safety stuff we've been doing actually says things that go a long way to proving it linearizable to a set. The only problem is the emptiness check, which is part of the POP, is somewhat difficult to even intuitively get a handle on why that works, why it is saying it's empty when it is, and conversely. So the other thing I wanted to take away is ICAP good for this sort of proof? And it works. Well, it works to a point of me being able to get an informal proof outline out. But the fact that we're having to say everything that happens on this entire stack when we're talking about an update from one pointer to another pointer with some side conditions is a little worrying. Certainly in a separation logic context, you'd want to be able to frame off everything that isn't affected. So something I admittedly don't know much about but should be looking at more is the sort of separation or separation style logics that are deliberately created for reasoning about trees, because what we have is effectively a tree, not a linked list. So that's all I really wanted to say. I'd be happy to take questions, and my email is up there if you have a couple of seconds for jotting it down.
Questions for Matt?
Thanks very much, Matt. That's a great talk.
Thank you.
Well explained. Aaron, could you comment on the feasibility or likelihood of having a completely machine-checked proof in RCAP, which is Slack?
Okay. Do you want me to repeat the question? Or?
No. He's got a mic.
Okay, it's fine. So at the moment, ICAP itself has a mechanized proof of soundness, but at the moment there isn't, as far as I know, any tooling or support for automation of ICAP proofs. If there was that kind of tooling support, then certainly I would be very interested in getting an automated proof, because as I kind of hinted, there's a lot of umming and ahhing about whether I've actually got everything correct. If it was a mechanized proof, it would have to be up to the soundness of ICAP. Okay.
Did you consider other logics like divine brain,
Yes, Iris. Yeah, so there are a lot out there. So why did you choose ICAP? Did you evaluate others?
So I have to admit, I didn't do a full tour of all the available logics. The main reason I chose ICAP was mainly familiarity in the sort of general area. Certainly my supervisor, of course, kind of very knowledgeable on sort of ICAP on CAP-esque logics. So I'm certainly thinking it paid off, because I originally sketched a bit in normal CAP, and then the abstract, the sort of label transition systems of ICAP made the proof a lot easier to kind of to write. But as I said, there are definitely some things that would make me open to maybe using a logic that's more suited to tree style data structures.
So thanks. I also found the talk very interesting.
Thank you.
Just a sort of meta remark about choosing the logics, I guess. Given the amount of work it takes to do the proof, I guess it's not really feasible to do the proof like over and over again for many different techniques. But maybe one thing you could focus on is when you had this very nice slide where you essentially said what wasn't a good match, and which parts of the proof you kind of don't like, in a sense, in this style. So maybe you could get a feeling with these other techniques for whether they're likely to alleviate that problem. Maybe that's the thing to focus on. In the end, otherwise you'll kind of do all of the stuff that works again. I don't know the answer, but of course there are lots of people here who wrote the works, and maybe they can give you an impression for whether they would be a better fit in terms of, for example, the framing issues you have in the low-level parts of the argument.
Yeah.
That would be very interesting, I think.
Yeah, I think that's a good comment, yeah. Certainly, I think the time issue is part of the reason why I haven't done a tour of all possible logics. Certainly, I think you're right in kind of focusing on what could be better in a possibly more suitable logic is the way to go. Certainly, ICAP does. Obviously, ICAP's intended for more higher order and re-entrant programs of data structures, which this isn't necessarily. So maybe a lot of it could just be explained by the fact that I'm trying to use a logic for kind of A, whereas my stack fits in more in category B. But so far it's been very useful, if not entirely suitable, completely suitable.
Cool. Thanks for the nice talk.
Thank you.
So the second and final talk of this session is by Tyler.
So, hi everyone, my name is Tyler Sorensen. I'm a PhD student and I'm supervised by Ali Donaldson here at Imperial and James Brotherston at UCL. And so, like the title suggests, we're going to talk about weak memory behaviors on GPUs, and specifically weak memory behaviors that cause bugs in GPU applications. So, to give a brief overview, the current state of the art for reasoning about GPU programs under weak memory is through what I call hand analysis. That is, you have an expert in both weak memory and GPUs stare really, really hard at the code and look for patterns which could lead to weak memory, and then try to think about whether that weak memory would cause a bug in the application. So there are a lot of flaws with this method. It's tedious, it requires domain experts, and it's error prone. So we propose a new method for trying to find weak memory model bugs in GPU applications. Specifically, we propose a testing methodology based on stress and fuzz testing. So the concept's pretty simple. You have your GPU application, and you simply add our stress and fuzzing hooks to the application. And then you also add a post condition to the application, which checks to see if the output of the application is correct. That gives you an annotated GPU program. And then you simply run this annotated GPU program for many iterations, and you check to see if the post condition fails. So, as a concrete example, prior work showed that the book CUDA by example contained a dot product routine which had a weak memory model bug in it. So we downloaded this code, we ran it for 1 hour, it takes about 2 seconds per iteration, and without any stress, we never observed any post condition violations. However, when we add our stress and fuzzing hooks, we were able to see 396 runs which the post condition was violated. So we were able to observe the weak memory model bug in this application.
So what are the post conditions?
What was that?
What post conditions
Oh,
did you use here?
the post conditions are unique to the application. So in the dot product, the post condition was if the dot product computed on the GPU matched a reference implementation on the CPU. So yeah, it's unique per application. All right, so the roadmap for the rest of this talk. First, we'll go over some background on weak memory models and GPUs. Then we'll talk in detail sort of about our stress testing implementation. And then we'll go over some of our results. So what do we mean by weak memory models? Well, we actually had a good introduction during the first talk by Roland, but I'll go over it briefly again. So one way people like to think about weak memory models is through what are called litmus tests. That is, short executions with an assertion about the final state of registers. So there are several parts to litmus tests. First, you have an initial state. In this one, you have x and y being memory locations, and they're initialized to 0. Then you have a short concurrent program. And finally, you have an assertion about the final state of registers. And this particular test is known as message passing, or MP. And it checks how to implement a handshaking idiom. That is, the memory location x stores data, the memory location y stores a flag, and what we want to know is if thread 0 stores some data, then stores a flag, thread 1 then reads the flag, then reads the data. We want to know if it's possible to read stale data in thread 1. So how might we analyze this program? Well, a popular way of reasoning about concurrent programs is by just enumerating the inner leavings. So if we start enumerating the inner leavings, there's one inner leaving where thread 0 executes completely before thread 1, and then we can keep sort of mixing up the instructions, and we'd see there's 6 possible interleavings, and in none of the interleavings does the assertion get satisfied. So this is a property known as Lamport sequential consistency, and in this particular test, the assertion cannot be satisfied under sequential consistency. So can we assume that this assertion will never pass? Well, no. Alglov and others have reported that when they actually run this test on an ARM Tegra processor, they observe 41 million violations out of 5 billion test runs. So actual architectures do implement this sort of behavior. So this is what we mean by weak memory models. The architecture is essentially allowed to reorder certain memory operations due to out-of-order pipelines or complex cache hierarchies. So we call a weak behavior an execution that doesn't correspond to an interleaving of instructions. All right, so that's a bit of background on weak memory models. We'll briefly look at GPU programming model. The GPU programming model is a hierarchical model. At the very base, you have threads, which are much like CPU threads. These threads all have access to a region of memory called global memory. These threads are then grouped into what are called blocks, and each block has a disjoint region of memory called shared memory, and that's local to only the block. So now that we have, let's see, a bit of background, we can go over the exciting stuff, the stress testing details. So prior work showed that GPUs implement weak memory models, and they did this by taking a number of these litmus tests, these short executions, and actually running them on GPUs and observing weak behaviors. So one of the interesting things that they noticed is in order to observe weak behaviors, it required heuristics. In particular, they found one of the most effective heuristics was to put stress on the memory system while these litmus tests were executing. So I'm going to briefly cover that heuristic and how it was implemented in this previous work. To do that, we have 3 litmus tests here. We have message passing, which we looked at earlier, load buffering, which essentially tests to see if loads can be reordered with stores, and then store buffering, which Roland went over during the first talk. And so we won't go into too much detail about these tests, other than the thing to notice is each of these tests only have 2 threads, and they each only have 2 memory locations, X and Y. And so in the previous work, when these tests were ran on actual GPU hardware, they used this heuristic called memory stress. And in this heuristic, T0 ran T0's part of the litmus test, T1 ran T1's part of the litmus test, and then they allocated a bunch of extra threads which just looped reading and writing to a scratchpad memory. So if we look at how the memory was actually laid out in this heuristic, we had the X and Y of the memory location were actually placed randomly in a large array, and then it was assumed that all the locations around X and Y were scratchpad that these extra threads could loop reading and writing to. So can we extend this heuristic for applications? Well, not really, because in applications, the X and Y memory locations in applications, we might not have scratchpad memory around X and Y, and that, I think, is the key ingredient why in the previous work they were able to observe weak behaviors. So we need to have a more coarse-grained partition between our stressing and application threads. So instead of having partitioning at the level of threads, we partition at the level of blocks. And if you remember in the GPU programming model, blocks are groups of threads. And so we have the N blocks that were supposed to run the original application. They run the application, and they have exclusive access to the memory that they use in the application. Then for stressing the application, we allocate extra blocks, or groups of threads, and they have their own disjoint scratchpad memory that they can freely read and write to that doesn't bother the application. So what we're actually going to focus on now is the memory stress, the strategy for this. We have a lot of threads, and we have a lot of memory, and we want to know the best way to actually stress this memory to reveal weak behaviors in the application. So, oh yeah, and our goal is that we don't want to have any a priori knowledge of the application. We don't want a user to have to go in and specify the memory locations or the threads that could be subject to weak memory. So we want to develop a good general purpose memory stressing technique. And so to do this, we go back to our litmus tests, the one that we showed earlier, message passing, store buffering, and load buffering. And we use these as micro benchmarks to sort of try to develop a good stressing strategy that makes all of these appear frequently. So to investigate this, the first thing we look at is where to stress in the scratchpad. So we have a large scratchpad, and we want to investigate where we need to put stress. So remember that the litmus tests had an X and Y memory location. What we do is we instantiate these litmus tests for a variety of distances d, and d stands for the distance between X and Y in memory. And this is at the word size granularity. So X and Y might have, in this case, 2 words in between them than 3 words. Anyway, we do that for a large value of d. And then in our scratchpad, we have each location I. And what we do is for each litmus test instantiated at distance d, we try stressing a single location 1,000 times. Then we try running the litmus test 1,000 times, only stressing that location. And then we move on to the next location, try stressing that. Move on to the next location, try stressing that. So essentially, we have a nice sort of visualization of our results from this. I'll tell you quickly how to read them, and then I'll go over some examples. So this number up here is the distance d. That's the distance between x and y in the litmus test. Down here, we have the index stressed. And over here, we have the litmus test, MP, SB, LB. And how we're going to represent a weak behavior is if we observe a weak behavior, we'll put a vertical bar in the graph. And the length of the vertical bar corresponds to how many weak behaviors were observed. So in this case, it would say we were stressing index 64 in the scratch pad, and we observed weak behaviors for store buffering. So if we actually look at some samples, let's see. Okay, so here we're at distance 0, and this is testing a GTX Titan. Nothing interesting, but we can scroll up through the distances, and kind of boring, until we get to the magic number 32, as 32 is normally a magic number. And then we start to see weak behaviors starting to appear. What's kind of interesting is, at least for this one, it looks like SB and LB are occurring when stressing the same location. Message passing has less magnitude, but it still has some. We can keep scrolling through, and sort of the wavelengths all look the same for the next 32, and then we get up to 64 and they change. So the thing that I take away from this is that weak behaviors appear when stressing groups of 32 in the scratch pad. So if you stress index 32, you get roughly the same weak behaviors as stressing index 33. You get roughly the same weak behaviors as stressing index 34 up to the next 32 locations. And so, yeah, all of these are very nicely grouped in groups of 32. So is this the same for all architectures? So that was just one architecture. If we try going to a slightly older NVIDIA architecture, let's see. Scroll through, nothing in the first bit. So all of a sudden we reach 32 and we're not seeing weak behaviors. But luckily 64 is another magic number. And here, before these weak behaviors were appearing in groups of 32, now they're appearing in groups of 64. So that just shows you for different architectures, they sort of have different behaviors when deciding where to stress a scratch pad to reveal weak behaviors. All right, so because these are kind of fun, we'll look at one more. So this is actually for the most recent NVIDIA architecture. It's a GTX 980. And so this one is unique because here, even at distance 0, we didn't see weak behaviors for the other chips, but we get some noise on message passing kind of all the way through. We can keep scrolling. This one's another one of these 64 ones. But here we don't see the sort of breaking off into groups of 32 or 64 as much. In fact, it doesn't look like there's any groupings. But if we keep going, finally, let's see. Finally, our groups appear, and they're size of 64. So back to the presentation. Okay, so we have a couple of those. So yeah, what does this tell us? Like I said earlier, if we want to reveal weak behaviors, we don't need to stress every single location in the scratch pad. We can stress one in every 32 or every 64, depending on the chip. And so just some terminology, we call a contiguous region of 32 elements a patch. So now that we know that, what we want to do is, without knowing d, the distance, we'd like to be able to hit a nice sweet spot like this when testing an application, because we won't know the distance d in the application. But if we look, these sort of sweet spots for message passing kind of change. There's one in this patch, one in this patch, and one in this patch. So we have a lot of stressing threads. What you might think is maybe some of them, maybe we can split them up. Maybe we can try to stress different groups of 32. So let's see. Yeah, so if we want to check to see how many of these groups of 32 we can actually test, because if you test more, you have a higher chance that you hit a good one, but you also lower the amount of pressure that you put on that particular patch. So here's the result of trying to spread the stress across multiple patches. We try to spread the stress across up to 64 of these patches. And the y-axis is the number of weak behaviors appeared. Spread is the x-axis. And what you can see is you can't spread the stress very far before you start to lose a lot of your effectiveness. Message passing does a strange U-type thing, but the others stay pretty low. So if we sort of zoom in on the more interesting part, we can see a peak in all of the tests around 2. So actually randomly picking 2 of these patches and just stressing 2 of these patches seems to be the most effective at revealing weak behaviors for these micro benchmarks. Okay. So now we have a memory stressing strategy that is, like I said, randomly picking 2 of these patches and stressing it. Let's see, how well does it work? So if we have this new application, it's an n-body particle simulation in the Lone Star GPU benchmarks. We don't really know, we came into this not really knowing anything about this application other than it's documented to have some communication across blocks. We added a post condition which checks for the final location of the particles. And so we download this, we run it for an hour. We don't see any instances of the post condition failing. When we add our stress, though, we're able to see 48 iterations where the post condition failed. So our nice systematic stressing strategy was able to reveal bugs in this application. Now the next thing to ask is, does it matter how we stress? So we did a lot of work developing this stressing strategy. We looked for patterns, we made graphs. But what if you tried something simpler? So we compare this systematic stressing to 2 other stressing strategies. The first one we call cache stress, in which we allocate a scratch pad the size of the L2 cache, and all of the extra blocks just run along that scratch pad and do a read and write to every single location. And then we also implement one called random stress, where each thread randomly chooses a location and randomly does a read and write to the location. So how well do these stressing techniques work? Well, on our Lone Star application, cache stress does not yield any post-condition violations, and neither does random stress. So we can see for this particular application, it was our systematic stress that was able to reveal the weak behaviors. And so what about the dot product, the one that we showed at the very beginning? So on the GTX Titan, we saw that without stress, we didn't observe any post-condition violations. With the systematic stress, we did observe some. And I also included a GTX 980 chip here as well, where we were able to observe post-condition violations. So with the cache stress, we were able to observe 2 post-condition violations on the GTX 980. And with the random stress, we were able to observe just a couple violations. So this other stress can reveal weak behaviors, just not nearly the magnitude that we observe with our systematic stress. So our full experimental study, we've tested 4 chips across 3 major NVIDIA architectures. We have results from 3 more chips coming, tested 10 applications. And here we've just talked about 3 different stress settings for each application and chip combination. So yeah, total, there's 40 chip application combinations. We've been able to observe post-condition violations on 32 of those. And with the systematic stress, we were able to observe all 32 weak behaviors. With the random and cache, we were only able to observe post-condition violations on 8 of those applications. And the number of combinations where our systematic stress was most effective, that is, yielded the highest number of post-condition violations, it was most effective in 28 of the chip application combinations. So let's see. Quickly, some higher level results. We provided empirical confirmation of 3 bugs that were reported in previous work and identified 2 new weak memory model bugs in 2 new applications. And for future work, we want to look at using this framework to automatically insert memory fences and then benchmark the cost of memory fences on GPUs. So that's it. Where to start? I'll let you go. Well, you choose.
Okay. Thanks a lot. So, do you plan to do any tests on AMD or internal GPUs, in particular the latter with a shared memory? The CPU could be like very different behavior potentially. And with a new like level 4 cache as RAM thing.
Yeah. I think it would be interesting to extend this to CPUs. I'm just.
I'm talking about the GPU.
Oh, GPU.
Intel CPUs. And
So.
AMD GPUs.
Yeah, we have some of those GPUs. I haven't gotten around to testing them yet. We'll see if there's time. But I think it would be interesting, and I don't see why it couldn't be applied to those.
Hi, so am I right in thinking you came to this approach by trying just things in the space rather than some intuition about the underlying architecture that you're running?
Yeah, so actually we came to this systematic stress with me just poking around, trying different stresses. And I finally found something that kind of worked, and we then thought about why it worked and how we could sort of systematically arrive at that.
Ask a follow-on. Do you think that in the future this technique will continue to work for future devices?
Well, so in our results, we've tested it across 3 major NVIDIA architectures, so like from 2008 to 2015 chips. And it's, as you saw in the final slide, that our stressing strategy was the most effective across 3 generations of NVIDIA chips. And I do, think that this is a good methodology for coming up with a good stressing technique regardless of kind of the chip or the vendor. Yeah. So I've thought about that. The ones with size 32, the only thing I could find is that corresponds to a cache line in the L2 cache, the size of a cache line in the L2 cache. And that's documented in the CUDA programming guide. The other 2 chips have that patch size of 64. And I cannot find anything in the documentation that sort of has that size in it. So I'm kind of at a loss for microarchitectural details about why this is. Cache lines, memory bus width, those are words that I hear thrown around.
You started to say that you would like to try this in CPUs, but
The but is that I like programming GPUs. And we have lots of nice applications for GPUs that have these weak memory model bugs. So we can kind of try out our methods on these applications where we know they had bugs from hand analysis, and it's a nice way to sort of start out the project, I think.
Can you do anything to randomize or otherwise affect the application?
So I haven't thought of, I guess you could like intercept calls to malloc and sort of randomize it at that level.
We could add padding fields to structs miscellaneously.
Yeah, you could do that kind of stuff as well. I think that would be a good thing to investigate, because as we saw, usually when the distance between x and y in the litmus test wasn't high enough, you didn't observe any weak behaviors. So if you could sort of randomize that, then yeah, you would probably get a better testing result. Yeah, so it's something to think about.
So if you do not observe any of those things without your stress testing, are those programs correct or not?
Yeah, that's a really good question. We got that question a lot with the previous work as well. I think it depends on who you are and what you're using the application for. Video game designers might be okay with some of this. HPC people running massive, expensive simulations might not be. And in fact, now that we've actually run a lot of these applications for many hours on the GPU, we've observed 3 application chip combinations where we have observed condition violations with no stress. It happens very, very rarely, like 1 in every 3 hours or so. But we have observed cases that without stress, these bugs appear. So.
I actually think that not for the verification community, but for the kind of performance community, you could use this work as an argument for not having to worry about weak memory to some extent. Right? I mean,
yeah.
You know, if you've got one hat on, you might say, this stressing revealed a potential problem, so you should fix that potential problem. With another hat on, you could say, the stressing only just revealed the problem, and if you insert fences to avoid the problem, you pay massive energy costs and performance costs. So actually, you may not want to fix the problem. So I mean, there are a few ways to look at it. I think what we're trying to do is simply provide the means for getting the data you need to make your own mind action.
I mean, sort of, I can confirm this. It's like what I hear from the HPC guys. It's like, if we miscalculate a bit in our simulations, it's like we just don't care, right? I mean, often they say this. But I'm sort of not very happy with this explanation that, so, like, there should be some basic intuition to sort of why this works, right? I mean, if it's only as simple as saying, well, we keep the memory subsystem busy, so things that we have not touched will be buffered longer, and we observe sort of more out of order executions. Is it like, could we say at least something like this?
Well, I mean, going back to the microarchitectural question, I don't know microarchitecture very well, and I think we need to talk to some people who do. But yeah, I do think it must be something with the bus width or the cache lines that by sort of just really hammering these with memory accesses, you're causing them to move slower or quicker through the cache hierarchy.
Right. I mean, there have been so many works now that sort of try to formalize the semantics of these things. I don't know what is the status on GPUs, but for sort of hardware memory models, I mean, maybe one could try it there and see, I mean, how it behaves and how it relates to the models that are.
Yeah, it's worth looking into. Yeah.
It might also be affecting the hardware on the GPU, right? It actually does a lot of work at high memory latency. It doesn't have asynchronous mechanisms that you have on CPU, so it has to do it by running multiple works.
No more questions? So, shall we thank Tyler again? So we have another break until 5.
I have a couple more technical
should hopefully manage to keep to time. I'm aiming to stop after about 20 minutes or so. Feel free to like wave if I go over or something. Yeah, go on.
Well, welcome to the last session of the day. I'm glad you all made it. And our next speaker is John on overhauling SC atomics. I have no idea what that is, so it's quite a minute.
Okay. Right. Hello. I'm John. This is joint work with Mark and Ali. So the 30-second summary of this talk is that the C11 programming language defines a number of atomic operations and fences. Some of these are deemed sequentially consistent. And we find that the rules that define the semantics of these SC atomics, as they're called, are too complex, they're too weak, and they're also too strong. And in this talk, I describe our work where we propose how to fix this. So I'm going to start by telling you a little bit about the C11 memory model, and then our proposals for how to fix that. Then I'm going to tell you a bit about the OpenCL memory model and how we can fix that too. So the 2011 revision of the C programming language provides a number of atomic operations such as fetch and add, compare and swap, exchange, and just plain stores and loads, all of which act indivisibly, so they can be used for lock-free programming. An example of something you might write is this. What you attach to each of your atomic operations is a memory order. And the memory order is the programmer's way to control the degree to which the weak memory behaviors of the underlying CPU or GPU that the machine natively exhibits, how many of those weak behaviors can be exposed to the higher level. So with memory order relaxed, we're basically saying anything goes. You can have all sorts of reorderings and store bufferings and what have you. If we use memory order release or acquire or release acquire, then this gives us stronger guarantees. The strongest of all is sequentially consistent. This is the default. And you might expect that the sequentially consistent SC semantics would be nice and simple. At least that's how Lamport envisaged it. But the thing is, since you can mix and match all of these different memory orders in your single program, it turns out that the semantics of SC atomics is surprisingly complex. And it's this complexity that we're going to tackle here. The way the semantics of these atomic operations is given is via a trace-based semantics. These are concurrent traces because we're in concurrent C, and they're also called executions. And the way the semantics is built is such that you have two phases. The first phase generates an over-approximation of the executions that could happen, and it does this by considering each thread in isolation. It then combines the per-thread executions together and then looks at every execution as a whole and removes those that are inconsistent with the axioms that define the C memory model. To give a very quick example, this is message passing that Tyler very helpfully already introduced in his talk. So to give a semantics to this program, what you would do is you consider, let's say, the left-hand thread first. This can give rise to the following trace where we do a write that's non-atomic to the location x with value 42, followed by a write to y of value 1 using memory order release. This is, in fact, the only execution that this thread can ever do. On the right-hand side, we could read y at 0 using memory order acquire, and then stop because the if fails. Or else we could read y at 1 and then go on to read non-atomically x at 1. But since we're considering these threads in isolation, we don't actually know anything about what these values might actually be. So we over-approximate and we just put in, we index over all of these possible values, 8 and 7, 82, 1, 42, anything like that. Throw them all together, and we end up with a great big bunch of possible executions. Then we look at each in turn and see which of them is actually consistent with the axioms that the memory model defines. And it turns out that this one's okay, this one's okay, this one, well, this is nonsense because you could never possibly read y at 5 there, so that's no good. That one's also no good for various reasons. So the more detailed version of how you deem an execution to be good or bad, you'd say the execution is consistent with the if it satisfies all of these consistency axioms of the memory model, and then the overall semantics of the program P is just its consistent executions. This is a slight simplification because you also might find that P has a data race which has a faulty execution. Then the semantics of P would be anything. This is a complexity that doesn't have very much to do with the thrust of this work, so we won't worry about that too much. There's actually a slight complexity where it's not just a matter of this execution satisfying the consistency axioms, but rather there's an existential quantifier going on here. It's consistent if there exists this bunch of additional things where if you stick those onto your execution, then that extended thing satisfies the consistency axioms. That extended thing is called a candidate execution, and you obtain it like something like this. So here's a plain execution. We just have the program order edges here. It's called sequenced before program order. I've also thrown in some initialization events that provide the initial zeros for each location. And to get a candidate execution, you stick on additional edges like this. So you've got reads from, which I think Roland called source in his talk this morning, modification order, also called coherence order, or as Roland called it, store order. The S relation is quite interesting. This has to be a total order between all of the events that are annotated as being sequentially consistent. So then, faced with a bunch of these candidate executions, the axioms then look for specific shapes that these arrows form. So for instance, one of the axioms rules out this shape, where you have an RF edge going back to itself. You also can't have this shape or this shape. These axioms can be neatly encoded formally as the irreflexivity of a certain relation. This one and this one. In fact, all of the axioms of the memory model can be encoded as the irreflexivity of some relational expression. Well, that's not quite true. We also have some relations being empty. So what we're doing here, in a slight departure from previous work on the C11 memory model, is we're phrasing all of the axioms using the CAT framework of Jad Alglav, Luc Maranger, and Michael Tauschnich, where they say if you can phrase all of your axioms as the irreflexivity, emptiness, or acyclicity of a relational expression that is just formed using basically the propositional fragment of the relation calculus, then if you can do that, then your memory model can be efficiently simulated using their simulator, which is called Herd. So it just has to, Herd basically just has to then check for loops, and that's quite quick. So I'm not going to explain all of these axioms. I just wanted to put them up there so you could sort of see the magnitude of the kind of beast we're dealing with. I'm cheating a little bit because I haven't defined all of these things like HB and RB and so on. But those are defined on that slide, which I also won't explain. OK, so that's the C11 memory model. So what I'm going to do now is focus in on these SC atomics axioms. Oh, Peter, yes. That, yeah, well, you mean his Lem version? Yeah. Yes. Yes. Hull says so, yeah. I forgot to start my stopwatch. You keep a track on how long I'm going? I don't know. OK, so the next bit I'm going to focus on the just the SC axioms. So you'll notice that a significant portion of that last screen was taken up with these axioms that have something to do with this S relation. So we're going to study these. Now, they're rather complex, and the first thing we might try to see if we can simplify these at all is to look at this sore thumb here, which is clearly a bit different from the others. I should say that it wasn't that the C11 committee sort of wrote down these axioms like this and thought it was fine to leave this one looking a bit odd. It's very much an artifact of the fact that we've massaged all the axioms into this form that makes this so apparent and stick out like this. Anyway, so maybe we can simplify this by just replacing this with S. That would look a bit neater. And in fact, there's a precedent for doing this. Victor Vafiadis and some co-authors proposed exactly this change to the model in their POPL 15 paper. They had a different motivation. They wanted to improve the mathematical monotonicity of the model. But they proved that it's actually a perfectly sound change to make. So let's take on their suggestion. Because if we do this now, we see that all that we're saying about the S relation is it must basically be consistent with all of these R1 up to R7. So in other words, the model is saying there must exist, remember it's an execution is consistent if there exists this S, right? So we're just saying, oops, there must exist this S, total order, that's consistent with all of these R relations. Well, we can just say that all of those R relations, if we union them all together and restrict to the SC operations that this total order has to go through, that just has to be acyclic. That just has to be a partial order. If that's a partial order, then by the order extension principle, we can extend it to a total order, and that's exactly what we need. So that's quite neat. Why would we want to do that? Well, because this axiom is a lot faster to simulate than the previous one. Why is that? Because we know if the axiom no longer mentions S at all. We construct S sort of implicitly. We know that it would exist. And so we don't, when we're calculating whether executions are consistent or not, there's no need now to iterate over all of the possible S orders, all the permutations of the SC atomic events, if you like, when finding whether an execution is consistent or not. So the simulation time can be dramatically decreased, massively exponentially kind of thing. So this is, and in practice we showed this on the herd simulator. So that's nice. And as I said, the existing compilation schemes remain valid for this, so this is a safe change to make. But we can go further. So if I just unwrap that and we go back to this form for a moment, we investigated what happens if we remove this bit. I'm not going to tell you what this axiom actually means or what it means to take it away. I don't have time for that. But let's just suppose let's just suppose we can take it out. Peter. Can I save it until the end? There's a question.
Why is it okay?
It's okay to take it out because we have a proof that all existing compilation schemes remain valid after this change.
It makes the model slightly stronger.
It does make the model slightly stronger, but
you might then worry that some machines will actually give you that strength.
But in fact, they don't actually. They're not sensitive to this change. So we tested it on x86 and power. Do you know, Mark?
These are the SC atomics, so probably, but we haven't talked about that.
Yeah, probably. Right. If we can make this change, and we have an argument why it's okay to do this, then it just turns out then that this axiom becomes implied by this one, so we can get rid of that. These four then all fold together into a neat little single axiom, and they can combine with this one, and everything just collapses beautifully into a single axiom like this, where I've also done the change that I mentioned in the previous slide, where we just have this partial order version, so the thing is acyclic. This axiom then gives rise to a memory model that is far simpler for programmers to understand and use. it gets rid of, so by strengthening that axiom, it takes out a sort of a not very nice corner of the model that programmers may well find unintuitive anyway. Again, these compilation schemes, they don't mind it if we do that. This was actually one of the funny executions that we no longer allow. Anyway, if you look at the effect on the text, this is the original text of the specification for C11. This is what we suggest you could rewrite that as if you take our rewrite into account. And well, yes, it's a lot simpler, and the text isn't like suddenly very dense or anything. It's the same sort of style, just a lot shorter. So yeah, so we think that's quite nice. Not really. No, have we? No. Scott?
So, as the standard was written, it was fairly obvious that if you just use SC atomics, that you get SC behavior because there is a total order. Is that no longer seems quite so obvious?
If you just use SC atomics, that should.
And non-atomic race freeze. So you could expect this state of race freedom there.
The total order is gone from your formulas.
Yeah.
But you can argue that it still is there. Right?
Yeah. So to be honest, I think there is a case that perhaps keeping this simplification, but then perhaps the text to the standard, it's exactly the same whether you require this acyclicity constraint or if you phrase it in terms of there is a total order. It's mathematically the same. So yeah, it may be that writing the text to be to refer to the total order is in fact preferable intuitively, if that helps. I think.
This is stronger than there are fewer consistent executions. You have a whole I was talking skeptical. Yeah. But I can't put my finger on one. So maybe we should talk about it.
Pete?
So one of the sources of complexity in the original PSP entries was implementability on Italian, which is not one of the ones that you're checking against.
So I know you had an answer to that, didn't you, Mark?
I think we'll be okay.
My grandmother's designed it. You might be okay, but
Offer them for some, they're actually
How long have I got?
Until 5 past, including questions.
Okay. Very well. I've had most of my questions already, I think. Okay, I'm going to tell you a tiny bit about OpenCL. Then this will be much quicker. Okay, so as we saw in Tyler's talk, so OpenCL is this it's an extension of C11, and it's for programming heterogeneous systems made of CPUs and GPUs, FPGAs, and whatnot. And in OpenCL, threads are organized into a hierarchy where threads form a work group. Many work groups execute on a device, and then you have lots of devices that form your heterogeneous system. You also have a hierarchy of memory. So memory you've got a region of private memory that's only for one thread. You've got local memory that's only accessible to a work group. You've got global memory that's accessible to all devices. And you've got this funny extra global memory for fine-grained shared virtual memory buffers with atomic supports, so FGA region. And I'll explain this on the next slide. So pictorially, OpenCL memory regions look a bit like this. So you might have a thread and another thread. They both have their own private memory. They might be in a work group that has its own local memory. You might have another thread, and that's in the same device, and another thread that's in a different device. They can all access global memory, and there's this special portion of global memory called global FGA memory. These threads can communicate via local memory because they're in the same work group. These threads can communicate via global memory. If these threads try to communicate via global memory, that's an inter-device data race. You can do this because they can both access these locations, but it's not allowed. What is allowed is they can communicate via this special inter-device global memory. These atomic store operations are now annotated not only with a memory order but a memory scope, which restricts the memory consistency just to one part of this execution hierarchy. So you can enforce your consistency constraints within the work group, or just within the device, or globally. I had a few examples of how you can use these memory scopes. So you can just, if your two threads are in the same work group, then you can just use work group scope, and that will be fine. There are a couple more examples, which I think I'll just go over briefly. Skip kind of thing. Just illustrating. There's this natural concept of scope inclusion, where basically the two memory events are using scopes correctly, so that the scope of this guy is big enough to reach this guy, and the scope of this guy is big enough to reach this guy, wherever they exist in the hierarchy. And OpenCL defines similar rules for SC atomics as in C11. It just sort of copies and pastes them over, pretty much, about this total order S, blah, blah, blah. But because it's a bit worrying that you've got this sort of single total order S through all of the SC atomics, and yet some of these SC atomics might have their consistency sort of limited to a work group. Over here, it might be a bit weird to have a total order between this guy that's just scoped at its work group and this guy that's scoped at its work group, and it's a very long way away. They have this restriction that says all of the SC atomics have to use this massive global scope, and they have to access this memory that's visible to everybody. So this is a great big stonking restriction here. They soften it slightly by saying, oh, else, well, maybe you can just use device scope and not access this memory that's visible to everybody. But so they sort of stuck these sort of plasters on to make it hopefully work out. It has a number of problems because you can't really always tell which location which region of a memory location is in. The default, which is device scope, is therefore not always enough. It's non-compositional because it's a sort of whole program property. This is so that's a bit worrying. And it's very restrictive. You could never use work group scoped SC atomics at all. And we also found a case where even with these restrictions, you could still get some funny behavior, which I won't go into. Anyway, basically, we propose that we can do the same thing with the SC axioms that we did in C11, but in the OpenCL case, we just say that these constraints on the SC events only have to hold if those events have inclusive scopes. And we proved that this rule is okay for existing compilation scheme. We only know of one for AMD GPUs. And yeah, they satisfy this, which is nice. And if you change the standard to accommodate this change, then this great big wad of text becomes very much smaller. So, in summary, we simplified. We slightly strengthened some of the rules in the C11 and OpenCL memory models, but we argue that these strengthenings are sound, and they certainly give rise to a model that's much less complex and fixes these various weaknesses and over-strengthens. So thank you very much for your attention.
So back when we were talking about the simplification of the sort of 8 or 9 axioms down to 1, you were suggesting that the single axiom is more straightforward to explain, for example, to users who are programming with such a framework. How would you, if you were asked to explain to a programmer what that one axiom meant as opposed to the 7, how would you explain that one axiom?
I think I would. So if you well, a bit of a naff answer would be to say that this was how they explained the previous axioms. This was my attempt to, assuming that was a good style for programmers, which is not clear, but this is you could put it into text. But you probably can't read that though.
So you probably don't want to read that. Just give me a second to take a photo of that.
You can send you our paper.
Yeah.
We don't want people to look at the axioms, right? That ultimately, only people in this room should look at the axioms. I mean, what we want to do is improve the specifications. Let people write tutorials online that programs can actually understand, right? I mean, to me, the value of all this formalization is you go from this horrible text, you put it into same mathematics that experts can understand, you work with it in that same mathematics, and then you translate it back into text that the world can understand. But like Donald Cooper with his books, right? He processes all this stuff, and then he publishes this nice summary. In a way, we're trying to just fit analogies to it. And that's what we've done here.
I wanted to say one thing about compiler optimization, because we did think about it a little bit. In his 2015 paper, Victor Faedis pointed out that the current specification of SC atomics in the C11 memory model make some compiler optimizations invalid. And this change in the example he gives makes kills the example that demonstrates that they can't be that demonstrates a particular optimization can't be done. That doesn't mean it can't be done. It's just one data point.
So, another very interesting talk. Thanks. Maybe Peter, to some extent, answered this in one instance, but I guess a natural question to ask is why didn't they write the specification this way in the first place? So do you think the reason is that they had concrete scenarios in mind that the original spec allows that yours doesn't? Or is it really more, similar to what Alistair said, if you see this, if you rewrite this text into this mathematical form, then you can see more clearly what should be happening? I mean,
Can I answer?
do you have...
Yeah, go for it, Mark.
Sorry, if that's okay.
I don't mind to answer.
The initial specification had substantial holes around this particular set of axioms. There was a bug in these axioms where some of the lines that John presented were omitted, and they allowed executions within the memory model that violated one of the key sort of goals of the design, which was that if you program in a particularly restricted set of the language, you get SC behavior. That was violated. So at the last minute, in order to fix that, patch that up, essentially, they added some of these axioms in particular the ones we're talking about strengthening. And I argued for, I was there at the time, and I argued for a stronger set of axioms that were actually pretty much the ones we're presenting here, but they wouldn't have it at the time because they didn't necessarily believe it.
Okay, that's very interesting. Thanks.
Oh, you're stubborn. So you're keeping on going.
Thank you.
Just to add to that, so I have to understand what the design process for the original text was like, because it didn't involve, until we arrived, any mathematics or any relationship to implementation or any testing or really any validation of the text of the axioms beyond what could be done by some quite a small set of quite smart but not very mathematical guys reading it and thinking about it. What did they do? Well, pretty good job in the circumstances. but we've seen this and a whole bunch of other work since then which, in the course of trying to prove something about the model, has observed that actually it would be nicer if it was a bit different.
Is John owed another round of applause?
Yes.
I think he is. And I guess while we're here, thanks to helping organising the workshop. I'll let you did overrun. So it's right. So I'm very pleased that John talked about the C model because it means I don't have to explain it, or at least I'm just going to explain the fun bits of it. One of the motivations for the C memory model is really to support compiler optimizations or program transformation. And so an obvious question you might want to ask is, does it actually support the optimizations that you think it supports? Does it support the ones that you really want it to support? And the answer, as Victor and Francesco showed in their recent paper, is no, it doesn't. And so the model is kind of broken. So that sort of suggests that what we need is some sort of general kind of understanding of how program transformation works on this kind of model. And that's really what I'm going to talk about today, something that we've been working on. So yeah, the context here is it's relaxed memory, it's axiomatic semantics. We're talking about a fragment of C11 with some tweaks, which we passed through sort of the Oracle, Mark Batty over there, and he sort of says, yes, that is sensible or not. The reason we're tweaking it is partly because the model is very big, and partly because the models argue, I don't know if anybody really disagrees with this, the model is broken in some respects. So most importantly, the relaxed atomics are, the compositionality and relaxed atomics don't really go together. So we don't have any relaxed in our model. We could probably include it if we fixed the compositionality properties, but we're going to solve an easier problem for now. So the immediate aim here is sort of program transformation. So for example, compiler optimizations. We want to know whether it's okay to transform your program. We want a sort of general theory of that sort of thing. So the approach here is quite I'm sort of wary of saying this because I know there are actual denotational semantics people in the room, but it's sort of denotational-ish. It's sort of denotational. It's sort of basically we're sort of saying that a program fragment is sort of summarized by a set of things, a set of representatives, a set of histories actually. And if you have a relationship between those histories, then you have a relationship between the kind of observations you can make in a context. And the other thing to say is it's under construction. So with our circa 1995 under construction web logo there. So here's the overview. I'm going to talk about what it means to be a transformation and why we want it to be compositional. I'm going to talk a little bit about C11, although I'll skim very quickly past that because you've already heard a lot of C11 so far. I'll talk about how we define histories, which are our kind of summaries of contexts, and then I'll talk about how we can cut down the context, because really we want to have as few of these things as possible. So this is the kind of world that we're in here. We've got programs, and we've got the semantics of programs, which are sets of executions. We're also in a world where we have contexts. So these are syntactic contexts. They're like a piece of C code where one of the blocks has a kind of please fill in later kind of hole in it. And we've also got program fragments, which you could sort of see as just a sort of C block. And I'm going to ignore for the moment any questions about whether it's syntactically okay to like stick things in other things. I'm just assume that we're allowed to kind of glue together context and program fragments. And what do we get when we stick a program fragment together with a context? Well, we get a program. Well, that's very nice. So really, we want to think about fragments because we don't want to have to think about the whole program when we're changing a program. We want to just be able to look at a little window and alter it in kind of one go. So my picture of what a compiler optimization is you're taking one fragment, sort of P1, and you're replacing it with P2. And that's sort of, you're performing some kind of rewrite of a bit of the program, and the rest of the program stays unchanged. So here's an example optimization, maybe it's an optimization, I don't know, but it's a transformation anyway, of a C program. We're going to read the value of X, and then we're going to read the value of X, and then when we transform the program, we're going to chuck away one of the reads. So we didn't do anything with the value of the first read. And so it sort of seems like, certainly in the sequentially consistent world, it seems like we shouldn't be able to, as long as R isn't something that's globally visible, it seems like this should be fine. However, relaxed memory ought to have made you suspicious of your intuitions and whether up is down or black is white. And so we need to be quite careful here. Unless I've said otherwise, everything here is release acquire, because that's really the kind of core of the model that is kind of everyone agrees is fairly sensible. So we kind of want to say, is this a sound transformation on C11? Is this something that it's okay to do? Well, first thing, we probably need to ask, what does it mean to be a sound program transformation? Well, okay, so I'm going to say a sound program transformation is where you have this property. Sorry for the splurge of mathematics, but it's really not a very complicated property. It's really just observational refinement. So what we're going to say is that for all of the contexts, if you have an execution of the program after you perform the transformation, and you have an execution, then there must exist an execution of the prior program where the observations are the same in the two executions. So everything you can do after you transform the program, you could also have done before you transform the program. And you have, I'm also going to very dishonestly skim over what I mean by an observation here, but that does actually matter quite a lot. So what we really want to have here is a sort of summary of all the possible interactions, a kind of set of things, which is a kind of, in fact, these are going to be, I'll call these histories. This is a kind of denotation. It's sort of a set of things that represents the behavior of a piece of code. And we want it to be sort of a local thing. So we just want to kind of just tease out exactly which bits of the interactions matter. And we want to have this property here. We want to have adequacy. So if the set of histories for P2 is included in the set of histories for P1, we also want it to be true that in all of the contexts we have this observational inclusion property. And that would mean that we could go, well, okay, so I can check my set of histories are related, and therefore my compiler optimization is sound. You know, job done. I'm going to get a bottle of water. I left it over here. So that's what we really want. We'd also sort of medium strongly like finiteness for for this sort of set of histories. So if you have a piece of loop-free code, you'd like to know that the set of histories here is finite, and that would mean that you could just automatically check inclusion, like, for example, check it in an SMT solver. That's something else we're thinking about. So this is all kind of, you know, noble goals. So what is it about C11 that makes this hard? Well, so C11, as John was saying, basically you have multiple partial orders on memory actions, and your executions are really kind of very monolithic things. You have a big thing, and you have a load of relations, and you don't really know, you don't really have a kind of incremental way of constructing the relations, although there are attempts to build those sort of things in the works. So you have a set of memory actions, you have a reads and writes, a read from relation. You have this relation happens before, which John skimmed over, but basically it's kind of the temporal order in as much as there is one in a relaxed memory model. And you have per location coherence, which is kind of over total order over individual writes. So even when you don't have a happens before, you certainly will know that individual writes are related by modification order. So what is it that makes this really hard to kind of come up with a kind of compositional way of dealing with these optimizations? Well, the C model is very non-compositional. It's very, in one sense, what you do is you build a big execution, and then you say, well, does this satisfy all of my axioms? Well, I mean, that's just fundamentally not a kind of compositional process. You're kind of like picking all of the whole of the execution in one go. And the validity axioms really assume that. So, you know, you really are intended to kind of look at the whole thing in one go. And that's part of the reason that actually testing the C semantics is also quite difficult. So validity forbids lots of things, but I mean, it also, well, here's an example of an axiom which I think John had, but basically it says things like you can't read too far into the past. So if you have a write and you have a write and you have a read, then you're not allowed to read from the earlier write if they're ordered in happens before. And that's sort of morally, it's because it's been overwritten later in time, because happens before is the time order. So, but the fact that reads generate happens before edges. So if we have a read, that kind of induces a kind of time order if it's a release acquire. And that means that the reads have a semantics which is not just reducible to their values. It's not, you can't just look at the values like you can in, for example, the Brooks semantics. And that's because the ordering on things really has an effect. So here's an example of where the ordering that's created by a read has an effect on your behavior. So we've got a kind of code block here that we want to sort of consider its effect on the surrounding context. And here we've got a write and another write and a write to x. Now, if we've got a read of y here, we want to ask whether it's okay for y to read 1. Well, in order to answer that question, even if this piece of code doesn't set any values, doesn't sort of return anything, we have to ask what's going on inside it. And that's because this piece of code could have a reads from edge, and it could generate a happens before. So if you have this happens before edge here, then there's an intervening write here, which according to the axiom I showed you on the previous slide, this read is obliged to see. So it's banned from seeing this one here. However, if we delete this read, it's perfectly valid to read from the earlier write. And so therefore kind of the writes have a kind of power in a relaxed memory model, which they really don't in a kind of sequentially consistent model, or at least it sort of is much more implicit in a sequentially consistent model. So yeah, here are the challenges. Sort of the semantics is whole program and axiomatic. There's sort of no notion of a global state, so we can't do the Brooks semantic trick of kind of just reading all the variables in a sort of magic operation. And it's sort of unclear which of these orders really matter, which of them can be observed by contexts. So that's really the problem. So we sat around, and we've actually been thinking about this for literally years, and we got a bit stuck, and then we thought the best way to make progress in computer science is plagiarism. And the best kind of plagiarism is when you plagiarize yourself, because then no one can complain about it. So basically, what we did was we had this paper about library abstraction a couple of years ago. And when you think about it, library abstraction, sort of replacing a library with its specification, that's really a kind of program transformation. What you're really doing is you're replacing a library implementation with a piece of specification code, abstracted code. And so our idea really, fundamentally, is to treat code transformations as a sort of generalized library abstraction. The difference is that your libraries and clients only interact through their call and return points, whereas here you've actually got overwriting shared variables. So it's actually not completely trivial to generalize it. But this is where we got the idea from. So here's the kind of gut feeling, the intuition of it. You've got an execution here, and it's execution of a piece of code, a syntactic context, and a piece of code fragment. Well, it must be possible. We can show it's possible to carve it up into sort of two pieces. But there's going to be some edges that kind of cross this fringe here. And really what we're going to be doing is we're going to be projecting to the important ones of these edges. We're going to be carving out just these edges here between the code and the context in the execution. So really the art of this is kind of working out which of the edges really actually matter in this case. In fact, the majority of these are projections of happens before. The majorities are things that are kind of part of this temporal order. But it turns out that we actually have to throw in a little bit more than that in order to make it work. So the first thing to say is we're only going to hold on to interface actions. So these are actions in the context which read and write to the same locations as the ones that are written inside the code fragment. So for example, if we have this kind of context here, we're going to hold on to read of y, but we're not going to hold on to read of z. And we're going to hold on to write of x, but again, we're not going to hold on to write of z. And that means we can, and we're also going to chuck away all the syntactic sort of structure in the context. So we're just going to sort of assume reads and writes floating in space. So that's a kind of easy case. We're also going to kind of hold on to this thing here, which kind of says where the call and return points for the code block are. And that's just because we need to know where to paste it back into the context. So now we've got kind of the more interesting bit, which is suppose we have a read inside the code, and we've got a write outside the code, and we've got a reads from between the two of them. Well, we certainly don't want to record that this read is here, because that would mean we can't transform the program at all. But we want to be able to kind of record that it has some effect, because we know that the context can see it. So what we're going to say is we've got an edge from the write to the read to the return, and we're going to record that thing in the history, that write to return edge here. So from the point of view of the history, this is what the code block looks like. It's not going to record that internal interaction. So again, if we've got a write and then we've got a read, we've got a write of x, a read of x, and we're going to, there's this edge from the call to the write to the read, and we're going to generate this edge here, which is in the history. So again, from the point of view of the code, this is what, the context, this is what the code block looks like. We're not going to record anything that happened inside it. Sometimes the order of things inside the code block is actually significant for the context. So if you have a write of x, and then you have a read of x, and a write of y, and a read of y, well, we've got a happens before edge like this. And so we're going to end up generating in the context this edge here. This is part of the effect of the program, and so we have to record it. We're also going to get these two edges here, which are just from the result of following call to write to read, write to read to return. We're also going to have more sort of subtle things. So it clearly matters. If we have a write of x and then a write of x, we can't order this read in the context before this read in the context, because otherwise we'd end up basically be reading backwards, and we'd sort of be reading out of order with respect to what the code block was doing. We don't want to expose the fact that these two writes are in order. So we're going to induce something in the kind of context which will represent that fact. So that's not a happens before. It's a kind of don't happens before here. These can be partially ordered or they can be ordered the other way, but you have to kind of have a sort of, don't put anything here sort of edge. So that's going to be something we call a deny, which sort of prohibits a happens before edge. So, and we're also going to have these edges here from the call to the read, And so this is now what this piece of code looks like. We've got these kind of deny edges between the kind of context reads and writes. And that means we can start building our set of histories. So history, the type is we have a set of interface actions. We have a happens before projection, which we'll call a guarantee. And we've got a forbidden happens before, which we're going to call a deny. And that means that then our set of histories is just a set of histories. And when we want to build the set of histories, we generate executions of the code block plus some very limited context. And then we just kind of generate the histories from the code block plus that limited context. How much more time do I have? 5 more minutes. So now maybe we want to validate our example in that case. So we've got this example here. We want to go from P1 to P2. And basically, now we know how to do that. We've got a theorem which helps us do it. So we go from P2 to P1 here. And so if we want to do that, well, we're going to find something in P2, and we show that it's still in P1. OK. So let me just pick a sort of representative-ish thing. You're going to have to trust me. This is sort of fairly representative of kind of the sort of shapes of execution you can have. Well, we have a write and we have a read, and then therefore the history is going to look like this. So now we need to ask, can we replicate this precise history using the other piece of code? And the answer is obviously yes. We just point this read of x to the write of x here, and what we end up with is exactly the same history, because the two reads froms just both generate edges to the return, and so we can throw away the rest of the thing about the reads. OK, so very, very quickly, we don't want to consider all contexts because there's an infinite set of them, and infinite sets are really awkward. And we really want to cut down the context pretty aggressively because there's lots of stuff in the context. If you only have one write, you don't need infinitely many or even 30 billion different contexts to kind of represent all of the context interactions. So the question here is, which contexts matter? All contexts? No, we definitely don't want all contexts. That would be really, really bad. So we've already said one way we can cut the context down. We're going to chuck out all of the reads and writes which are to locations which aren't written in the code. OK? So we'll just throw them out. And we're also going to chuck out all the stuff that's inside the code. Suppose we've got two reads from the same write. Well, in some sense, we're not learning anything more from from the two reads. We're just reading the same value twice. So we don't ever need to consider contexts where we read from the same write twice. So that cuts it down on context quite a lot. Suppose we've got a context where we have a write, and we have a write, and we have a read here. Well, the read comes from the write, and the write is in the context, and so we're not learning anything about the piece of code, so we'll just chuck that one out as well. So this one's a bit subtle. So it turns out, to my mild surprise actually, you can't just chuck out all of the writes that are unread you have to hold on to some of them. I can explain afterwards if you're interested why. Basically, you have to hold on to a single unread write for every write that is read. And so in modification order. So what that means is if we have a write here, and we have a modification order write and a modification order write, these two are sort of redundant. But if we chuck away one of them, then we still need to hold on to this one, which is kind of awkward, but it's still, because it's only for MO, because all of these will be MO intervening with writes that are read, and they're only read inside the code, we're still going to end up with a finite set of them for each sort of code block kind of behavior. But that's sort of slightly awkward thing I'm not quite satisfied with. But it turns out that if we have this property, cut the interface actions, the RF distinguished reads, and we just hold on to the interface actions, the RF distinguished reads, and the MO distinguished writes, then if P is a piece of loop-free code, and we have some assumptions about kind of value abstraction, so basically if we end up with a sort of finite set of kind of executions just for the piece of code on its own, then the set of executions which satisfy this cut X predicate, which satisfies, which dictates the number of contexts we're looking at, is also finite. So the set of histories is also finite. So that's really cool. So we've got kind of like a finite thing, representation of the code, which allows us to kind of reason about it. So that's really what we've been up to. The current status, still work in progress. We've proved adequacy for a fragment of C11, which is release acquire, and some stuff with non-atomics. We're still fighting a bit with C11's safety DRF properties. You need sort of a prefix semantics, essentially. We're working on SC. I mean, as John was saying, it's a bit unclear which SC semantics you really want. We validated a whole bunch of optimizations. We've got this finiteness theorem, which is, I'm convinced that the theorem is true. I'm not sure the proof is right, but we've got a full abstraction result in progress for a kind of generalized version of the theorem. And the checking tool is in the planning stages, by which I mean we've said that it would be a good idea to have it, but haven't done anything about it. So that's it. And thank you very much for listening.
Thanks for the talk. Seems like really cool ideas. I want to understand the top level idea. So you want to be able to do compositional program transformations ultimately, is that right?
Yeah.
So that means that a compiler would say, there's this bit of code, I'd like to do some optimization on it. I know that it calls some procedures or that there's a loop that I don't want to have to analyze. And I would like to be able to get some sort of summary of what that code might do, say.
Yeah, essentially the point is that you want... Okay, so the first thing to say is that compiler optimizations are not always compositional in this way. Sometimes they're whole program. But suppose that you're doing something like a really simple thing like read elimination, where you have a redundant read. You want to know that sound on the model, irrespective of where you put it in the program. So
okay, so I was going to ask, does this require like whole program knowledge, even though, does this require either having the code of those contexts, or does it require having summaries for the context that have been somehow computed? Or is this something you can really apply if you're doing separate compilation, where you need maybe compiling this particular C file and then years later linking it with another C file?
I mean, the objective, and I mean, there are a few sort of side assumptions, like you have a kind of manifest of. Let me think about it. No, it's precisely that. So any syntactic context you place this code into, you can optimize it soundly, and it won't have you'll have this observational refinement property. So you won't be able to see any new behaviors, irrespective. So you can kind of so you can do optimization on a kind of per file basis.
Right.
I mean, the extent to which real compiler optimizations fit that pattern, and the extent to which they kind of look at lots and lots of, they actually do depend on the context, is a bit unclear to me. So, but there are certainly some optimizations that have that structure.
There was a comment you made at the start about the C11 concurrency semantics being whole program, and that being difficult for compilers. But it occurred to me that actually a lot of the C semantics are whole program. For instance, it's illegal in C to divide by 0, say, and it's illegal to read from uninitialized memory. But that's in the context of the whole running program from main to some point. It must not read from invalid memory, or it must not divide by 0. And in general, when you're compiling a function, you've no idea where the function would have been called from. So I mean, I would say that all compiler implementations basically are having to work with these global constraints. This thing of the semantics being global doesn't seem to be specific to concurrency. Is it more troublesome that it's global in the concurrency setting?
I suppose that, I mean, I would sort of expect in the case of a sort of sequentially consistent world that you could kind of take the sort of the states of the kind of variables at the start of the thing and kind of do the kind of Brooks trick of kind of taking kind of different snapshots or during the execution and sort of use that to validate your optimizations. So it's sort of, you don't, I suppose the distinction I was trying to make with whole program versus kind of, you know, other kinds of semantics was more that you don't really have sort of prefix closed operational semantics that kind of, you can just sort of build up your executions bit by bit by bit, because that sort of, in some sense, makes your task as a kind of, if you're trying to understand how the semantics works, much easier, because you can sort of run the piece of code from its start to its end, or maybe sort of add some extra stuff onto it. Whereas the C semantics is much more kind of, you have this kind of big thing, which is just kind of like a chunk of execution, and you have to kind of deal with it.
So I guess in simplistic terms, in the beginning of entry to a procedure with SC, you could say, well, you don't know what's happened, but we know this at this interleaving point, and we can analyze. But in the
Peter's about to disagree with me about this, I think, but it's yeah. I think there was a question behind you, actually.
I mean, can you say something about the size of this cut-down context set?
Yeah, sure. So basically, you need to consider there's potentially at most one read for every internal write, and at most one write for every pair of internal writes or read writes. So it's so that what that means is it's sort of it's not many. Yeah, it's polynomial. Yeah.
Sort of combined with the full abstraction result, you would actually get a sort of complexity result for your observational refinement, right?
Yeah.
That would be cool.
Yeah. Well, it's well, the full abstraction thing is kind of we're sort of unclear how important it would be, but it would be interesting if there are sort of applications that we could think of it. That would be very cool. Yeah.
Okay. Disagree with you now. Well, first comment. So Kindle Nienhouse, who isn't here today, now has an operational but equivalent model for C11. You were speaking as if that would help. It's not at all clear. It's very strange. It's not at all clear that that would help. So that is still a global semantics. It's not defined sort of compositionally, inductively on the syntax in a denotational fashion.
Yes.
So that doesn't immediately help you with what you're trying to do here.
Yeah. Okay. Yeah. Maybe that was. Maybe that isn't right. Yeah. I mean, it is. You do sort of want. I mean, I've sort of shied away from using the word denotational here because, like I say, that has sort of actual technical meanings that I don't want to sort of travesty. Sorry.
Seems good to me.
But I mean, it's sort of. Well, I mean, the reason it's not a denotation is because you don't have a parallel defined for it. So you can't kind of stick two of these history sets together and generate another history set, right? But it is very denotational in sort of flavor, and you would like to be able to do this sort of syntactic kind of syntactically on the structure of the piece of code, really. If
So the other thing you well, maybe you mentioned, but I missed. So the thing which is totally non-compositional is the race-free part of the C11 definition.
Yeah,
So you're only talking about consistent execution sets there.
So the reason I didn't mention that is because we're still fighting with it. So I think what we need is sort of some sort of I mean, the reason, I mean, maybe this fits with your point that sort of operational semantics doesn't help you completely here, but we sort of need a prefix semantics if you're going to do the safety reasoning in a sensible way. So you sort of say something like, well, for those that don't know, if you have a data race in a C program, then your whole program has no semantics. It's not just that particular execution, it's everything. It's kind of what they call catch-fire semantics, which is a wonderful image. And so the way that you kind of have to deal with it in our system is that you have to say, for every execution of the sort of pre-transformation piece of code, which has a kind of data race in it with respect to its context, then you have to find one in the post-transformation piece of code which has a data race with respect to its context and has the same sort of history prefix. So you could always get to the same place, sort of more or less. Yes, sorry, the other way around. Yeah, the same post-transformation piece of code, the pre-transformation piece of code. I always get them mixed up because you do the inclusion the other way around. Yeah, so basically you need to sort of say, you need to have matching kind of faults with respect to the context. That doesn't present too many problems sort of formally, but it's sort of a bit awkward because it just ends up being a bit, you're sort of quantifying over these prefixes, which is not very pleasant.
But so on that, you might really want to talk to Kim about, because understanding in what sense the axiomatic model is incrementalizable. Is most of what he's done.
Well, I think Mark has some construction which is sort of prefixing, but that's different from.
You have a question?
Sorry. Very nice. I like it. I wanted to know if I understood something. So, when you started off drawing the pictures, seeing what happens when we plug things in and how we can describe the behaviors in terms of the dependencies, in terms of reading rights. I mean, firstly, if you ignore the interesting parts, you start off just with these sets of read and writes that depend on the initial and return points in the code. And then you add these edges, right? You add these dependency edges and the deny edges. And then you have, I thought I saw where this was going, and then I was a bit surprised, and then I thought maybe you did it anyway, actually. So I kind of expected this is going to be like a logic, right? We're going to have assertions now which basically describe these conditions. You describe the set of things you depend on, describe the deny, all this kind of thing.
Yeah.
And now we're going to see rules that check that. But I guess maybe that's, in a sense, what you have with these sufficient representations of the interesting contexts. In a sense, you have a symbolic description of, I mean, as you say, an infinite number of things, right? But in a way that you can reason about. Does thinking of this as a logic make sense? In particular, does it make sense to think about like strengthening and weakening these specifications? Do you need to check that sort of point-wise you have one in the corresponding set, or would it be enough to say, okay, there's one that's stronger or weaker? I can't think which way around the condition should be.
Well, I mean, one way that I sort of cheated in this presentation was you actually can weaken the sort of by dropping edges as you become more abstract. Yeah, I mean, I think it's a perfectly legitimate way to think of this. Is you're relating a piece of code to a sort of more abstract, sort of like a specification. Yeah. And so, I mean, this talk is entirely free of separation logic or indeed any kinds of logic whatsoever. But I mean, really, the aim is to give ways of reasoning about a piece of code that summarizes its interactions with the surrounding context. And a logic would be one way of doing that. Yeah.
Could you pass the microphone?
So, coming back to this finance assumption and acyclicity, so what happens if it's cyclic? Is it, or sort of more concretely, could you imagine a theorem that says, if I distinguish by context, I unwind each loop twice at most, and then, if there is a context distinguishing the two implementations, then it will already see this on this twice unwound loop.
Oh, so you mean sort of if each of the loop unwindings, subsequent loop unwindings is sort of in some sense the same, right? Yeah, I suppose so. I mean, it's sort of morally, there's no reason why you would need to unwind it more, because it's sort of, it has this regular structure. Oh, we haven't thought about that at all, but yeah, it would be really interesting to try and do that, yeah.
So we have a question from our virtual audience. So Ilya Sergey is asking, Gottman, Yang and others had to generalize call return histories in some ways to account for ownership transfer and in specifications of sequentially consistent concurrent libraries. Do you foresee doing something similar in this line of work?
That would, well, okay, let me say, we haven't thought about it, and ownership transfer is quite subtle on a relaxed memory model. So I would be, because you don't really have kind of a notion of kind of like state to transfer. But I don't know, I mean, it's sort of, this is really kind of more of a sort of semantics kind of piece of work than a kind of reasoning piece of work. And if we had a reasoning system like GPS or something like that, it seems perfectly likely that you'd be able to kind of glue the two together and end up with something that's kind of a resource, something that lets you kind of deal with kind of resource transfer on a kind of relaxed memory model. That would be very cool if we could make it work.
Any more questions? Any more questions here? Okay.
Can we do a comment? Hello, Ilya.
Hello, Ilya, and thank you for the question.
So should we thank Mike? Thanks everyone. So that ends the first day. So we'll start again tomorrow, I think at 9 o'clock. The plan now is we have dinner at Med Kitchen for anybody who wants to join. That's at 7 o'clock, Med Kitchen on Gloucester Road. And before that, anybody who wants to is welcome to go to the pub, and the
nominated pub.
The nominated pub is the Imperial College Union Bar, which is in the Fight quadrangle.
I have to go.
Can I suggest that can I have a volunteer of Imperial if who knows where that
honestly
is?
it's probably easier to, I don't know if there's really very much more to talk about. I mean, the only thing to say is that I'm going to go and talk to Ralph and Derek next week and the week after. So I'm going to try and sort of pin down sort of more precisely what it is that they're planning on working on and what it is that sort of something that, so everyone can have something fun to work on, you know.
Then totally